Let's begin by understanding what we mean by an AI operating system and why this concept matters today more than ever. For the past few years, most people have interacted with AI as a tool. Whether it's ChatGPT, image generators, or APIs, these systems are typically used in isolation. You give an input, you get an output, and that's where the interaction ends. But that model is rapidly changing. We are now entering a new phase where AI is no longer just a tool, it's becoming a system. Instead of one-time interactions, we are building environments where AI can continuously think, act, and improve over time. This is what we refer to as an AI operating system. An AI OS is not a single model or application. It's a combination of multiple components working together: agents that make decisions, memory that stores context, tools that execute actions, and interfaces that connect everything to users or external systems. The key idea here is integration. Rather than solving one task at a time, AI operating systems are designed to handle entire workflows, from understanding a problem to executing a solution, without constant human intervention. This shift is similar to how traditional operating systems changed computing. Instead of running one program at a time, operating systems allowed multiple processes to run together in a coordinated way. We are now seeing the same transformation happen with AI. And throughout this course, you won't just learn how to use AI, you'll learn how to design these systems. To fully understand AI operating systems, we need to look at how AI has evolved over time. There are 4 major phases in this evolution. The first phase is tools. These are standalone capabilities, like chat models or APIs, that perform a specific function. They are powerful, but they operate in isolation. Each interaction is independent, with no awareness of what came before. The second phase is workflows. Here, we start connecting tools together into sequences. For example, one tool generates content, another processes it, and another publishes it. This is where automation begins. However, these workflows are still rule-based and rigid. They follow predefined paths and struggle when something unexpected happens. The third phase introduces agents. This is a major leap. Agents are systems that can make decisions. Instead of following fixed rules, they analyze the situation and decide what to do next. This allows for much more flexibility and intelligence. Finally, we reach the fourth phase, AI operating systems. This is where everything comes together. Instead of isolated tools or individual agents, we now have fully integrated systems. These systems combine multiple agents, memory, tools, and interfaces into a single environment that operates continuously. The key difference here is persistence and coordination. AI operating systems don't just respond, they operate. And this evolution, from tools to systems, is what defines the future of AI. Let's take a closer look at the transition from tools to workflows. In the beginning, AI tools were used individually. You would give a prompt, get a result, and then manually decide what to do next. Each tool operated independently, with no shared context or coordination. While this approach works for simple tasks, it quickly becomes inefficient for complex processes. This is where workflows come in. Workflows connect multiple tools into a sequence of steps. Instead of manually handling each stage, the system automates the flow from one step to the next. For example, you might generate text, then summarize it, then send it somewhere, all automatically. This is a big improvement. However, workflows have limitations. They rely on predefined rules. Each step is fixed, and the system follows a specific path, regardless of changing conditions. If something unexpected happens, like missing data or a different input format, the workflow can break. This is why workflows are often described as brittle. They work well when everything goes as expected, but they lack flexibility. Another limitation is the lack of intelligence. Workflows don't make decisions, they simply execute instructions. So while workflows bring automation, they don't bring adaptability. And that's exactly why the next step in evolution, agents, is so important. Now we reach one of the most important transitions in AI systems, the shift from workflows to agents. Workflows, as we discussed, follow fixed rules. They execute predefined steps without understanding the broader context. Agents, on the other hand, introduce decision-making. Instead of being told exactly what to do at every step, an agent evaluates the situation and decides what action to take next. This is what we call the autonomy leap. Agents are context-aware. They can analyze inputs, interpret goals, and dynamically adjust their behavior. This allows them to handle more complex and unpredictable tasks. For example, consider the difference between a script and an AI assistant. A script follows instructions exactly as written. If something changes, it fails. But an AI assistant can adapt. It can understand variations, handle ambiguity, and choose the best course of action. This adaptability is what makes agents powerful. They don't just execute, they reason. They can break down tasks, prioritize actions, and iterate based on results. This is a fundamental shift in how systems are designed. Instead of building rigid pipelines, we start building intelligent entities that can operate independently. And once you have multiple agents working together, you unlock the next level: systems. The final step in this evolution is moving from individual agents to full systems. At this stage, we are no longer dealing with isolated components. Instead, we are designing ecosystems where multiple agents collaborate to achieve complex goals. Each agent has a specific role. Some handle planning, others execute tasks, and others monitor results. Together, they form a coordinated system. But agents alone are not enough. To function effectively, they need memory and tools. Memory allows the system to retain context across interactions. This means it can learn, adapt, and maintain continuity over time. Tools provide the ability to take action, whether it's calling an API, running code, or interacting with external systems. When you combine agents, memory, and tools, you get a cohesive system that can operate continuously. And this is a key difference. Traditional systems are triggered. They run once and stop. AI systems, on the other hand, are persistent. They are always active, always processing, and always improving. This leads to an important mindset shift. Instead of thinking in terms of individual tasks, you start thinking in terms of systems. You design how components interact, how information flows, and how decisions are made across the entire system. And this is exactly what defines an AI operating system. Now that we've seen the evolution from tools to systems, let's clearly define what an AI operating system actually is. An AI operating system is a unified platform designed to think, act, and adapt continuously. Unlike traditional software, which runs only when triggered, an AI OS is persistent. It operates in an ongoing loop, processing information, making decisions, and taking action in real time. At its core, an AI OS is made up of 4 key components. First, agents. These are the reasoning engines of the system. Agents interpret goals, plan actions, and execute decisions. They are what give the system intelligence. Second, memory. Memory allows the system to retain context across interactions. Without memory, every interaction starts from zero. With memory, the system can learn, personalize, and improve over time. Third, tools. Tools are the execution layer. They allow the system to interact with the outside world, whether that's calling APIs, querying databases, running code, or triggering workflows. And finally, interfaces. Interfaces connect the system to users and other systems. This could be a chat interface, an API endpoint, or even a voice-based interaction. What makes an AI operating system powerful is not just these components individually, but how they work together as a cohesive whole. The system doesn't just respond, it operates, continuously adapting and improving. Let's take a deeper look at the core components that make up an AI operating system. Starting with agents. Agents are responsible for reasoning and decision-making. They don't just execute tasks, they plan, prioritize, and adapt. In a real system, you might have multiple agents, each specializing in a specific role, such as planning, execution, or monitoring. Next is memory. Memory is what transforms a system from reactive to intelligent. It allows the system to retain both short-term and long-term context. Short-term memory handles the current task, while long-term memory enables learning, personalization, and continuity across sessions. Then we have tools. Tools are how the system takes action. These can include APIs, code interpreters, search engines, or any external capability. Tools bridge the gap between intelligence and execution, allowing the system to move beyond thinking into doing. Finally, interfaces. Interfaces define how users and external systems interact with the AI OS. This could be through a user interface, a chatbot, voice commands, or APIs. The key idea here is coordination. Each component plays a distinct role, but the real power comes from how they work together seamlessly to create an intelligent, adaptive system. Now let's understand what makes an AI operating system fundamentally different from traditional systems. The first difference is intelligence versus automation. Traditional systems automate predefined steps. AI systems, on the other hand, can reason, adapt, and make decisions dynamically. The second difference is adaptability. Traditional systems are static. They behave the same way every time. AI operating systems are adaptive. They evolve based on context, inputs, and past interactions. The third difference is interconnectedness. In traditional systems, components are often siloed. In an AI OS, components share context and work together. Agents, memory, and tools are tightly integrated, allowing for coordinated behavior across the system. And finally, persistence. Traditional systems are typically one-shot. They run when triggered and then stop. AI operating systems are always on. They continuously process information, respond to events, and improve over time. These differences are what make AI operating systems the next generation of software. AI operating systems are not just theoretical. They are already being used in real-world applications. One of the most common examples is AI copilots. Tools like coding assistants or writing assistants are embedded directly into workflows, helping users think, create, and execute tasks more efficiently. Another example is customer support automation. Modern systems can handle end-to-end support processes, triaging requests, routing them, and even resolving issues without human intervention. AI research assistants are also becoming increasingly popular. These systems can search, analyze, and summarize large amounts of information, helping users generate insights at scale. And in enterprise environments, AI systems are being used to automate operations across departments like finance, HR, and operations. These systems coordinate tasks, manage workflows, and provide decision support. What's important to understand is that many of these systems are already evolving toward AI operating system architectures, even if they are not labeled as such. Let's wrap up this module with some key takeaways. First, AI is evolving from tools to systems. What started as isolated capabilities is now becoming fully integrated environments that operate continuously. Second, agents are the foundation of intelligence. They enable systems to reason, make decisions, and adapt to changing conditions. Third, memory is essential for context. Without memory, systems remain stateless and limited. With memory, they become capable of learning and improving over time. And finally, AI operating systems represent the future of software. Instead of building static applications, we are moving towards systems that think, act, and evolve. This shift requires a new mindset. Instead of focusing on individual tasks, we need to design systems that are intelligent, adaptive, and scalable. And that is exactly what you will continue to build throughout this course. In this module, we shift from understanding what AI systems are to how they are actually built. At a high level, every AI system, no matter how simple or complex, is made up of a few core building blocks. As shown in this introduction, these components are agents, memory, tools, and interfaces. Think of these as layers in a system. Each layer has a specific responsibility, and together they create something far more powerful than any individual component alone. Agents are responsible for intelligence. They decide what to do. Memory provides context. It allows the system to remember what has happened before. Tools enable execution. This is how decisions turn into real-world actions. And interfaces define how users or other systems interact with the AI. What's important here is not just the components themselves, but how they work together. An AI system is not just a model, it's an ecosystem. Throughout this module, we'll break down each of these components and understand how they interact to form intelligent, scalable systems. Let's now look at how these components are structured within a system. As shown in the architecture diagram, AI systems are typically organized into 4 layers. Each layer plays a distinct role. At the top, we have the decision layer. This is where agents operate. This layer is responsible for reasoning, planning, and deciding what actions to take. Below that is the context layer, which is memory. This layer stores information about past interactions and provides the context needed for intelligent behavior. Next is the execution layer, which consists of tools. This is where the system actually performs actions, calling APIs, running code, or interacting with external systems. And finally, we have the interaction layer, which includes interfaces. This is how users and systems communicate with the AI. This layered architecture is powerful because it enables modularity. Each layer can be improved or replaced independently without breaking the entire system. This is what makes modern AI systems scalable and flexible. Let's start with the most important component, the agent. Agents form the intelligence core of any AI system. They are responsible for reasoning, planning, and decision-making. As highlighted on the slide, agents interpret goals and context, break down complex tasks into smaller steps, and decide what action to take next. This is a major shift from traditional systems. Instead of hard-coding every possible path, we allow the agent to dynamically decide how to achieve a goal. This makes the system far more flexible and capable. Agents are not just reactive, they are goal-driven. They operate with an objective in mind and continuously adjust their behavior to achieve it. In more advanced systems, you may have multiple agents working together, each with a specialized role. For example, one agent might handle planning, while another handles execution. But regardless of complexity, the core idea remains the same. Agents are what give AI systems their intelligence. Now let's look at how agents actually operate. Agents follow a continuous loop, often described as input, plan, act, observe, and iterate. It starts with input. The agent receives a goal or a task. Then it moves into planning, breaking that goal into actionable steps. Next comes action. The agent executes those steps, often using tools. After that, the agent observes the results. It evaluates what worked and what didn't. And finally, it iterates. Based on the feedback, it adjusts its approach and continues working toward the goal. This loop is what makes agents adaptive. Unlike static systems, agents can learn from their actions and improve over time. They are not limited to a single execution. They continuously refine their behavior. This ability to iterate is what allows agents to handle complex, real-world problems. Now let's talk about memory, the component that gives AI systems context. Without memory, every interaction starts from scratch. The system has no awareness of what happened before. This makes it limited and inefficient. Memory changes that. As shown on the slide, memory enables context-aware behavior. The system can respond based on previous interactions, making it more intelligent and relevant. It also enables personalization. By remembering user preferences or past behavior, the system can tailor its responses and actions. Another key benefit is session continuity. Memory allows the system to maintain coherence over time, even across multiple interactions. This is especially important in complex workflows where context must be preserved across multiple steps. In short, memory transforms an AI system from reactive to intelligent. It allows the system not just to respond, but to understand, adapt, and evolve over time. Now that we understand why memory is important, let's look at the different types of memory used in AI systems. There isn't just one kind of memory. There are multiple layers, each serving a different purpose. First, short-term memory. This holds the current context of a session, what's happening right now. It allows the system to stay consistent within a conversation or task. Next is long-term memory. This is persistent. It stores information across sessions, enabling the system to learn over time and retain knowledge beyond a single interaction. Then we have vector memory. This is particularly important in modern AI systems. Instead of storing exact matches, vector memory enables semantic retrieval. In other words, it finds information based on meaning, not just keywords. And finally, external storage. This includes databases, logs, and file systems. These provide scalable and structured storage for large amounts of data. Each of these memory types plays a role in making the system more intelligent, more contextual, and more capable of handling real-world complexity. Let's now move to tools, the execution layer of an AI system. Tools are what allow the system to act. Up until now, we've talked about reasoning and memory. But without tools, an AI system can only think. It cannot do anything in the real world. Tools bridge that gap. They take decisions made by agents and convert them into real actions. For example, an agent might decide to fetch data. A tool would then call an API to retrieve that data. Or the agent might decide to perform a calculation. This could be handled by a code execution tool. Common examples of tools include APIs, code interpreters, and web search. The key idea is that tools extend the capabilities of the system beyond its internal reasoning. They allow the system to interact with external systems, access real-time information, and perform meaningful tasks. Without tools, AI remains theoretical. With tools, it becomes practical. Now let's talk about interfaces, the layer that connects the AI system to the outside world. Interfaces define how users and systems interact with AI. The most common interface today is the chat interface. It provides a conversational experience, allowing users to interact naturally with the system. But interfaces go beyond chat. APIs allow systems to communicate with each other. This enables AI to be embedded into larger applications and workflows. We also have voice and graphical interfaces, which create more immersive and interactive experiences. The choice of interface has a huge impact on user experience. A well-designed interface makes the system intuitive and accessible. A poorly designed one can limit its effectiveness, no matter how powerful the underlying system is. So while interfaces may seem like the outer layer, they play a critical role in how AI systems are used in the real world. Now let's bring everything together. An AI system is not defined by a single component. It's defined by how all components work together. As illustrated in the diagram, there is a continuous feedback loop between agents, memory, tools, and interfaces. The agent decides what to do. Memory provides the context needed for that decision. Tools execute the action, and the interface delivers the output back to the user. But the process doesn't stop there. The system observes the results, updates its memory, and the cycle continues. This continuous loop is what makes the system intelligent and adaptive. It's not a one-time execution. It's an ongoing process. And this integration is what transforms individual components into a real production-ready AI system. Let's wrap up this module with the key takeaways. First, AI systems are built on 4 core components: agents, memory, tools, and interfaces. Each component has a distinct role. Agents provide intelligence. They reason, plan, and decide. Memory provides context. It stores and retrieves information. Tools enable execution. They turn decisions into actions. And interfaces enable interaction. They connect the system to users and other systems. But the real power comes from integration. No single component creates intelligence on its own. It's the combination and continuous interaction of all 4 layers that makes an AI system truly capable. This layered approach is what allows us to build systems that are scalable, adaptive, and ready for real-world use. And as you move forward in this course, you'll start applying these components to build your own AI systems from the ground up. In this module, we move from understanding components to actually designing intelligence. Because here's the key idea. An agent is not intelligent by default. Its behavior is designed. As introduced on this slide, prompts, decomposition, and reasoning are the 3 core mechanisms that transform a raw language model into a reliable agent. A model on its own can generate text, but it doesn't inherently know how to behave in a structured, consistent way. That's where design comes in. Agent behavior is defined by how it thinks, how it makes decisions, and how it executes actions. And each of these aspects is controlled through deliberate design choices. This means that 2 systems using the exact same model can produce completely different results, depending on how they are designed. Throughout this module, we'll focus on how to shape that behavior intentionally. Because in real-world systems, reliability doesn't come from the model. It comes from the architecture you build around it. Let's go deeper into why agent design is so critical. As highlighted on the slide, the model itself is not the main variable. The real difference comes from how the system is structured. You can take the same model and build 2 completely different agents. One might be inconsistent, unpredictable, and difficult to scale. This is what we see with poor design. Unclear prompts, no structure, and no reasoning framework. The other can be reliable, predictable, and production-ready. This comes from good design, clear instructions, defined roles, and structured execution. This is an important mindset shift. Instead of asking, which model should I use? You should be asking, how should I design this system? Because design determines behavior. A well-designed agent produces consistent outputs, handles edge cases better, and integrates more effectively into larger systems. In contrast, a poorly designed agent may work in demos but fail in real-world usage. So, if you want to build production-grade AI systems, agent design is not optional, it's essential. Now let's define what actually makes an agent intelligent. As shown on the slide, behavior is the result of three things: how an agent thinks, how it decides, and how it acts. First, thinking. This is where reasoning frameworks come in. The agent processes context, evaluates options, and forms an understanding of the task. Second, deciding. This is controlled through structured prompts and constraints. These define what the agent is allowed to do, what it should prioritize, and how it should behave. Third, acting. This is where task decomposition plays a role. Complex goals are broken into smaller, executable steps that can be completed reliably. And finally, all of this is designed. None of this behavior happens by accident. Every output the agent produces is a result of intentional design choices. This is a critical concept. You are not just prompting a model, you are engineering behavior. And that is what separates casual usage from real system design. Now let's look at the foundation of agent behavior, the system prompt. The system prompt defines the identity of the agent. It answers three key questions: who the agent is, what it should do, and how it should behave. First, identity. This defines the role of the agent, whether it's a planner, an assistant, a reviewer, or something else. Second, goals and rules. This defines what the agent must achieve, as well as constraints, what it should not do. And third, tone and format. This determines how the agent communicates and structures its outputs. The system prompt is the first and most important design decision you make. A weak prompt leads to vague, inconsistent behavior. A strong prompt creates clarity, structure, and reliability. Think of it as setting the foundation of a system. If the foundation is unclear, everything built on top of it becomes unstable. But if the foundation is strong, the entire system becomes more predictable and easier to scale. Building on system prompts, the next step is role design. As shown on the slide, assigning roles to agents is similar to how high-performing teams operate. Each member has a specific responsibility. In AI systems, this translates into specialized agents. For example, a planner agent focuses on breaking down goals into steps. An executor agent focuses on completing tasks. And a reviewer agent checks outputs for quality and correctness. This separation of responsibilities improves performance. Instead of one agent trying to do everything, each agent focuses on what it does best. This also makes systems more modular and scalable. You can improve or replace one role without affecting the entire system. Another benefit is clarity. When roles are clearly defined, agents produce more consistent and predictable outputs. This is especially important in multi-agent systems, where coordination is key. So rather than building one generic agent, you design a system of specialized agents, each contributing to the overall goal. And this is where agent behavior starts to become truly powerful. Now that we understand the importance of system prompts, let's talk about how to actually write them effectively. A strong system prompt is not vague. It is structured, explicit, and intentional. As shown on the slide, there are three key elements you must define. First, the objective. This is the primary goal of the agent. It should be clearly stated, with no ambiguity. The agent should know exactly what it is trying to achieve. Second, constraints. These define boundaries. What should the agent avoid? What assumptions should it not make? Constraints are critical for controlling behavior and preventing errors. And third, output format. This is often overlooked, but extremely important. By specifying how the output should be structured, whether it's JSON, bullet points, or a step-by-step format, you make the agent's responses more predictable and easier to use downstream. The slide also highlights the difference between weak and strong prompts. A weak prompt might say, "Help the user and be useful." This is too vague and leads to inconsistent results. A strong prompt, on the other hand, clearly defines the role, the task, and the output structure. The takeaway is simple. Clarity equals reliability. The more structured your prompt, the more consistent your agent will behave. Now let's move to task decomposition, one of the most powerful techniques in agent design. As shown in the diagram, complex tasks can overwhelm agents. When you give a model a large, ambiguous task, it often produces incomplete or inconsistent results. Task decomposition solves this problem by breaking the task into smaller, manageable steps. Instead of asking the agent to do everything at once, you guide it through a sequence. First, define the complex goal. Then, break it into subtasks. Each subtask is simpler, clearer, and easier to execute. Once these steps are defined, the agent executes them one by one, producing a final result that is more accurate and verifiable. This approach improves reliability because each step can be validated independently. It also improves traceability. If something goes wrong, you can identify exactly where the issue occurred. In short, decomposition reduces complexity and increases control, two critical factors in building production-ready systems. Not all tasks are the same, and that's why there are different decomposition strategies. As shown on the slide, there are three main approaches: sequential, hierarchical, and parallel. Sequential decomposition is the simplest. Tasks are executed step by step, where each step depends on the previous one. This works well for linear workflows. Hierarchical decomposition is used for more complex problems. A large task is broken into smaller subtasks, which may themselves be broken down further. This creates a tree-like structure. Parallel decomposition is used when tasks are independent. Multiple subtasks can be executed at the same time, improving efficiency and speed. Choosing the right strategy depends on the nature of the problem. If tasks are dependent, use sequential. If they are complex and nested, use hierarchical. If they are independent, use parallel. Understanding these patterns allows you to design systems that are both efficient and scalable. Now let's talk about structured reasoning, the mechanism that drives intelligent decision-making. Raw text generation is not enough for building reliable systems. Agents need a structured way to think. As shown on the slide, one of the most effective frameworks is the plan. Act, observe, loop. First, the agent plans. It defines an approach before taking action. Next, it acts. It executes one step at a time rather than attempting everything at once. Then, it observes. It evaluates the outcome of its actions. And finally, it adjusts. Based on what it observes, it refines its approach and continues. This loop enables the agent to adapt, self-correct, and improve over time. It also reduces errors, because the agent is constantly validating its own progress. Structured reasoning transforms an agent from a text generator into a decision-making system. Let's bring everything together. As shown in the pyramid on the slide, intelligent agent behavior is built on three layers: prompts, decomposition, and reasoning. At the base is the system prompt. This defines the identity, goals, and constraints of the agent. It sets the foundation for everything else. On top of that is task decomposition. This provides structure. It breaks complex problems into manageable steps. And at the top is structured reasoning. This drives execution. It determines how the agent thinks, acts, and adapts. Each layer adds a dimension of intelligence. A strong prompt ensures clarity, decomposition ensures reliability, and reasoning ensures adaptability. When all three are combined, you get agents that are not just functional, but production ready. And this is the key takeaway of this module. The model is just the engine. Architecture is what makes it intelligent. Let's wrap up this module by reinforcing the most important ideas you should take away. The first and most critical concept is this. Agent behavior is designed, not emergent. An agent does not become intelligent on its own. Every output it produces is a direct result of the architecture you define, your prompts, your structure, and your reasoning framework. If the design is weak, the behavior will be inconsistent. If the design is strong, the behavior becomes reliable and predictable. Second, system prompts define identity. The system prompt is not just an instruction. It is the foundation of the agent. It determines who the agent is, what it is trying to achieve, and how it should behave. A well-defined prompt creates clarity and consistency. A vague prompt leads to confusion and variability. Third, task decomposition drives reliability. Complex tasks are one of the biggest sources of failure in AI systems. By breaking tasks into smaller, well-defined steps, you reduce ambiguity and increase accuracy. Decomposition also makes systems easier to debug, test, and scale. Fourth, structured reasoning enables intelligence. Frameworks like plan, act, observe give agents a way to think systematically. Instead of generating outputs blindly, the agent evaluates its actions, learns from feedback, and improves over time. This is what transforms an agent from a simple responder into a decision-making system. And finally, the most important perspective shift. The model is just the engine. The real intelligence comes from how you design the system around it. As you move forward, focus less on chasing better models and more on building better architectures. Because in real-world AI systems, design is what determines success. And that's exactly what you're now equipped to do. Design agents that are not just functional, but production ready. In this module, we move from designing agents to understanding how they think. Because the reality is, intelligent behavior does not come from a single response. As introduced on this slide, truly capable agents rely on multi-step thinking. They don't just answer once, they go through a process. This is a fundamental shift. Most basic AI interactions are single shot. You ask a question, and the system generates an answer. But real-world problems are rarely that simple. They are layered, ambiguous, and often require multiple steps to solve correctly. This is why multi-step thinking is essential. Instead of generating a single output, agents must plan, execute, evaluate, and refine their approach continuously. This transforms them from simple responders into problem solvers. And throughout this module, we'll break down exactly how that works. Let's start with the problem. As shown on the slide, single-step responses fall short when dealing with real-world complexity. Most real problems are multi-layered. They require analysis, decision-making, and validation, not just a one-time answer. A single response cannot capture all of that. Another limitation is the lack of iteration. Without iteration, the system cannot correct itself. If the first output is wrong or incomplete, there is no mechanism to improve it. This is why we introduce the concept of the thinking loop. Instead of responding once, the agent operates in cycles. It plans what to do, executes actions, observes the results, and then adapts. This iterative process is what transforms an agent from a static system into a dynamic one. So the key takeaway here is simple. If you want intelligent systems, you need loops, not single steps. Now let's look at the core architecture that enables this behavior, the intelligence loop. As shown on the slide, This loop consists of 4 stages: plan, act, observe, and iterate. First, planning. The agent defines an approach and breaks the goal into manageable steps. Next, action. The agent executes those steps using tools and structured logic. Then, observation. The agent evaluates the results, checking for correctness, completeness, and alignment with the goal. And finally, iteration. Based on what it observes, the agent refines its approach and continues. This loop is what makes the system adaptive. It allows the agent to learn from its actions and improve over time. Instead of guessing once, the agent continuously moves closer to the correct solution. And this loop is the foundation of every reliable AI system. Let's zoom into the first phase, planning. Planning is where the agent defines its strategy before taking action. As highlighted on the slide, the first step is understanding the goal. The agent must clearly define what success looks like. Next, decomposition. The agent breaks the problem into smaller, actionable steps. This reduces complexity and makes execution more reliable. And finally, defining a strategy. The agent decides the sequence in which these steps should be executed. This phase is critical. If the agent jumps directly into execution without planning, it increases the risk of errors and inconsistencies. Planning ensures that the agent has a clear roadmap before it begins. And in complex systems, this step often determines the success of the entire process. Now let's move to the action phase. This is where the agent begins executing its plan. As shown on the slide, the key principle here is executing one step at a time. Sequential execution reduces the risk of compounding errors. By focusing on one step, the agent maintains clarity and control. Another important aspect is using tools. Agents don't operate in isolation. They leverage tools such as APIs, code execution, or data queries to perform tasks. These tools allow the agent to move beyond reasoning and actually interact with the real world. Finally, consistency. The agent must follow structured patterns during execution. This ensures that outputs are predictable and reliable. The action phase is where decisions become results. But without structure and precision, even the best plans can fail. And that's why execution must be controlled, step by step, and intentional. Now we move into the third phase of the loop, observation. This is where the agent evaluates the results of its actions. As shown on the slide, observation is not optional. It's essential for intelligent behavior. The first step is checking correctness. The agent must determine whether the output is accurate and aligned with the original goal. Next, identifying gaps. Even if the output is partially correct, what's missing? What is incomplete or unclear? And finally, gathering feedback. This is where the agent collects signals that will guide the next iteration. This phase is what enables self-correction. Without observation, the agent would simply continue executing blindly, repeating mistakes and compounding errors. But with observation, the system becomes aware of its own performance. It can detect when something is wrong and adjust accordingly. This is what separates a static system from an adaptive one. Now we reach the final phase, iteration. Iteration is where improvement happens. As shown on the slide, the agent uses the insights from observation to adjust its approach. The first step is dynamic adjustment. The agent modifies its plan based on what it learned from the previous step. Next is retry or improvement. If a step failed, the agent doesn't stop. It refines the strategy and tries again. And finally, continuation. The loop continues until the goal is fully achieved. This is a key concept. Agents don't need to be perfect on the first try. Instead, they become effective through iteration. Each cycle brings the system closer to the correct solution. And this is what makes multi-step agents powerful. They improve as they operate. Now let's talk about how this loop helps in handling complex tasks. As shown on the slide, complex problems require more than a single step. They require decomposition and iteration working together. A large task is first broken down into smaller steps: research, analysis, and summarization, for example. Then, each step is executed within the loop: planned, executed, evaluated, and refined. This combination allows the agent to handle problems that would be impossible in a single pass. Decomposition reduces complexity. Iteration improves accuracy. Together, they allow the system to scale to real-world challenges. This is how agents move from simple tasks to complex problem-solving. Now let's focus on making agents more robust through error awareness. As shown on the slide, intelligent agents must be able to detect when something goes wrong. The first capability is failure detection. The agent must recognize when an output is incorrect or does not meet the goal. Second, flagging issues. Not all outputs are equally good. The agent must distinguish between acceptable results and poor ones. And third, retry strategies. Instead of stopping at failure, the agent should rephrase the problem, adjust its plan, or try a different approach. This transforms the system from brittle to resilient. Error-aware agents don't just execute, they monitor themselves and recover when needed. And this is critical for real-world systems, where perfect execution is rarely guaranteed. Let's bring everything together into a design pattern. As shown on the slide, reliable agent systems are built on three key pillars: structured prompts, task decomposition, and the iteration loop. Structured prompts guide behavior at every step. They ensure clarity and consistency. Decomposition breaks down complex goals into manageable steps, making execution more reliable. And the iteration loop provides continuous feedback, allowing the system to adapt and improve. Together, these elements create agents that are not just functional, but intelligent, adaptive, and scalable. The key takeaway is this: agents are not defined by a single response. They are defined by how they think over time. And when designed correctly, they don't just solve problems. They continuously improve at solving them. Let's wrap up this module by reinforcing the most important ideas. The first key takeaway is that multi-step thinking is essential. Real intelligence does not come from a single response. It comes from a process, an iterative loop that allows the agent to refine its understanding and improve its output over time. Single-shot responses may work for simple tasks, but they fall short when dealing with real-world complexity. The second takeaway is the importance of the plan, act, observe, iterate loop. This loop is the engine of intelligent agent behavior. Planning defines the strategy, action executes the steps, observation evaluates the results, and iteration refines the approach. This cycle allows agents to continuously move closer to the correct solution. Third, iteration enables improvement. An agent does not need to be perfect on the first attempt. What matters is its ability to learn from feedback and adjust. Each iteration reduces errors, fills gaps, and improves alignment with the goal. Over time, this leads to more accurate and reliable outcomes. Fourth, error awareness builds robustness. In real-world systems, failures are inevitable. What matters is how the system responds. Error-aware agents can detect when something goes wrong, flag incorrect outputs, and apply retry strategies. This turns fragile pipelines into resilient systems. And finally, the most important mindset shift. Intelligent agents think in loops, not single steps. This is a fundamental change in how we design AI systems. Instead of expecting perfect answers immediately, We design systems that improve through iteration. Instead of static execution, we build adaptive processes. And instead of focusing on outputs, we focus on how the system thinks. As you move forward, remember this. The power of an agent is not in what it says once, but in how it reasons over time. And that is what makes multi-step agent thinking the foundation of truly intelligent systems. In this module, we move from designing individual agents to designing systems of agents. Because in real-world AI, one agent is rarely enough. As introduced on this slide, multi-agent systems represent the next evolution in AI architecture. Instead of relying on a single agent to handle everything, we distribute responsibilities across multiple agents. Each agent has a defined role, and together they collaborate to solve complex problems. This is similar to how human teams operate. In a high-performing team, you don't have one person doing everything. You have specialists, each focusing on a specific task, and a system that coordinates their efforts. The same principle applies here. Multi-agent systems combine collaboration, specialization, and orchestration to achieve outcomes that a single agent cannot. And as we move forward, you'll see that this is not just an advanced concept. It's becoming the standard for building real-world AI systems. So what exactly is a multi-agent system? As shown on the slide, it is a system composed of multiple independent agents, each with a defined role, working together toward a shared goal. These agents don't operate in isolation. They communicate, share context, and hand off tasks to each other. This coordination is managed by an orchestration layer, which ensures that the right agent is doing the right task at the right time. The key idea here is collaboration. Instead of one agent trying to handle everything, tasks are distributed across agents that are better suited for specific responsibilities. This makes the system more modular, more scalable, and more adaptable. And most importantly, it allows us to move beyond the limitations of single-agent systems. To understand why multi-agent systems are important, we need to look at the limitations of single agents. As highlighted on the slide, the first issue is overload. A single agent handling multiple responsibilities quickly becomes overwhelmed. As complexity increases, the quality of its output begins to degrade. The second issue is accuracy. Complex multi-step problems often exceed what a single agent can reliably handle. Without specialization or structure, errors become more likely. And the third issue is scalability. Monolithic agents are difficult to maintain, update, and extend. Any change affects the entire system, making it fragile and hard to evolve. These limitations are what drive the need for multi-agent systems. Instead of forcing one agent to do everything, we distribute the workload across multiple agents, and this leads to better performance, higher accuracy, and more scalable systems. Now let's look at why multiple agents are more effective. As shown on the slide, the first advantage is divide and conquer. Complex tasks are broken into smaller subtasks, each handled by a specialized agent. This reduces complexity and improves precision. The second advantage is parallel execution. Multiple agents can work at the same time, significantly increasing speed and efficiency. And the third advantage is specialization. Agents designed for specific tasks perform better than general-purpose agents. A focused agent can achieve higher accuracy and consistency. Together, these advantages make multi-agent systems more powerful than single-agent systems. They are faster, more accurate, and better suited for real-world complexity. Finally, let's explore the balance between specialization and generalization. As shown on the slide, general agents are flexible. They can handle a wide range of tasks and are useful for exploratory or unpredictable scenarios. However, they often lack depth. Specialized agents, on the other hand, are focused. They are designed for specific tasks and deliver higher accuracy and reliability. The best systems combine both. A general agent can act as a router or coordinator, understanding the problem and deciding what needs to be done. Then, specialized agents handle execution. This combination provides both flexibility and performance, and this is a key design principle in multi-agent systems. Use generalization for exploration and specialization for execution. Now that we understand the importance of specialization, let's look at how to design specialized agents effectively. As shown on the slide, a common pattern is to divide responsibilities into 3 key roles: planner, executor, and reviewer. The planner is responsible for breaking down the overall goal into structured subtasks. It defines what needs to be done and in what order. The executor takes those tasks and performs the actual work. This could involve calling APIs, generating outputs, or interacting with external systems. The reviewer ensures quality. It validates outputs, checks for errors, and confirms that the results meet the required standards before moving forward. This separation of roles is powerful. It reduces ambiguity, prevents overlap, and ensures that each part of the system is optimized for a specific function. Instead of one agent trying to do everything, each agent focuses on what it does best. And this leads to more reliable and scalable systems. Now let's explore how these agents collaborate. As shown on the slide, there are 3 primary collaboration patterns: sequential, parallel, and hierarchical. Sequential collaboration is the simplest. Agents pass outputs along a chain, one after another. This works well for workflows where each step depends on the previous one. Parallel collaboration allows multiple agents to work simultaneously. This is useful when tasks are independent and can be executed at the same time, improving speed. Hierarchical collaboration introduces a manager or supervisor agent. This agent coordinates other agents, assigns tasks, and ensures alignment with the overall goal. Choosing the right pattern is a key design decision. It directly impacts performance, reliability, and system complexity. Now let's talk about orchestration, the layer that holds everything together. Orchestration is responsible for coordinating agents and managing the flow of tasks across the system. As shown on the slide, orchestration performs several critical functions. First, it routes tasks. It ensures that each subtask is assigned to the correct agent. Second, it manages communication. It controls how agents exchange information and pass outputs between each other. Third, it controls flow. It determines sequencing, retries, and branching logic. And finally, it ensures coherence. It keeps the system aligned with the overall goal, even as multiple agents operate independently. Without orchestration, a multi-agent system would quickly become chaotic. With it, the system becomes structured, coordinated, and reliable. Now let's look at how agents communicate. As highlighted on the slide, one of the biggest challenges in multi-agent systems is information loss during handoffs. To address this, we need well-defined communication strategies. One approach is shared memory. In this model, all agents read from and write to a common context store. This ensures that information is persistent and accessible. Another approach is direct messaging. Here, agents pass structured outputs directly to each other. This is faster and more isolated, but requires careful design to avoid losing context. The key idea is to define clear communication contracts. Agents should know what information to pass, in what format, and how it will be used. This ensures consistency and prevents breakdowns in the system. Finally, let's look at how multi-agent systems are used in real-world applications. As shown on the slide, content generation pipelines often use multiple agents, one for research, one for writing, one for editing, and one for publishing. AI research systems use agents to search, analyze, and synthesize information. Customer support systems use specialized agents for triage, resolution, and escalation. And developer productivity tools use agents for code generation, review, testing, and documentation. In all of these examples, the same principle applies. A team of specialized agents working together is more powerful than a single agent working alone. And this is why multi-agent systems are becoming the standard in modern AI architecture. Let's wrap up this module by reinforcing the most important concepts. The first key takeaway is scalability. Multi-agent systems scale where single agents break down. As tasks become more complex, distributing work across multiple agents allows the system to handle higher levels of complexity without losing performance. Instead of overloading one agent, we distribute responsibilities across a coordinated system. The second takeaway is specialization. Focused agents consistently outperform general-purpose ones when it comes to well-defined tasks. By assigning clear roles, such as planner, executor, and reviewer, you improve accuracy, consistency, and reliability across the system. Specialization allows each agent to operate at its highest capability. The third takeaway is that patterns matter. How agents collaborate, whether sequentially, in parallel, or hierarchically, directly affects how the system behaves. The collaboration pattern determines speed, reliability, and complexity. Choosing the right pattern is not just an implementation detail, it is an architectural decision. The fourth takeaway is orchestration. A strong orchestration layer is what turns a collection of agents into a cohesive system. It ensures that tasks are routed correctly, communication is structured, and the overall system remains aligned with its goal. Without orchestration, even well-designed agents can fail to work together effectively. And finally, the most important insight: real-world AI systems are already multi-agent. From content pipelines to enterprise automation, production systems rely on teams of specialized agents working together. This is not a future concept, it is the current standard. So as you move forward, shift your thinking. Don't design a single powerful agent. Design a system of agents, each with a purpose, working together under a clear orchestration strategy. Because the future of AI is not one agent doing everything. It's a well-coordinated team of agents doing it better. In this module, we take multi-agent systems one step further by introducing structure. Because once you have multiple agents working together, the next challenge is coordination. As introduced on this slide, the supervisor worker architecture provides a centralized model for managing multi-agent systems. Instead of agents negotiating with each other directly, one central supervisor coordinates everything. This creates a structured, predictable system. Tasks flow through a defined hierarchy, from supervisor to workers and back again. This is a powerful pattern because it reduces chaos. Without structure, multi-agent systems can become difficult to manage. Agents may duplicate work, lose context, or operate out of sync. But with a supervisor, the system becomes organized. And this architecture is widely used in real-world distributed systems because it balances flexibility with control. Let's define this architecture more clearly. As shown on the slide, the supervisor-worker model is built around centralized control. One supervisor coordinates all agents. There is no need for peer-to-peer negotiation between workers. This simplifies communication and reduces system complexity. The architecture is also designed for multi-agent environments from the ground up. It supports many concurrent workers operating at the same time. And importantly, it enables structured execution. Tasks move through a defined hierarchy. The supervisor assigns tasks, workers execute them, and results flow back to the supervisor. This creates a clear and predictable system behavior. So instead of a network of loosely connected agents, you have a coordinated system with a clear control layer. Now let's understand why this model is so effective. As highlighted on the slide, the first advantage is simplified coordination. With a single control point, the system avoids the complexity of managing multiple agent-to-agent interactions. The second advantage is better observability. Because everything flows through the supervisor, it becomes the central place to monitor, log, and debug the system. This makes troubleshooting much easier. And the third advantage is scalability. You can add more worker agents without redesigning the system. The supervisor continues to coordinate tasks, regardless of how many workers are added. This makes the system horizontally scalable. These advantages are why the supervisor worker model is widely used in large-scale systems. Now let's focus on the supervisor itself. As shown on the slide, the supervisor is the brain of the system. It performs several critical roles. First, it acts as a decision maker. It interprets high-level goals and determines the overall execution strategy. Second, it decomposes tasks. It breaks complex goals into smaller, manageable subtasks. Third, it routes work. It assigns each subtask to the most appropriate worker agent. And finally, it monitors progress. It tracks execution, handles retries if something fails, and aggregates results into a final output. This central role is what enables coordination across the system. Without the supervisor, the system would lack direction and structure. Now let's look at worker agents. As shown on the slide, workers are the executors of the system. Each worker is designed for a specific function. Unlike general agents, workers do not try to handle everything. They focus on one task at a time within their domain. This makes them more efficient and reliable. Workers also operate independently. They do not need to know about other workers or the overall system. They simply receive a task, execute it, and return the result. And importantly, they return structured outputs to the supervisor. This allows the supervisor to process results consistently and maintain control over the system. This separation between supervisor and workers is what makes the architecture scalable, modular, and robust. Now let's focus on one of the most important responsibilities of the supervisor, task delegation. As shown on the slide, delegation starts with receiving a high-level goal. The supervisor then decomposes that goal into smaller, structured subtasks. Each subtask is clearly defined, making it easier to execute. Next, the supervisor routes each task to the most suitable worker agent. This is a critical step. Effective delegation ensures that each task is handled by the agent best equipped to perform it. It prevents overload on any single agent and ensures optimal use of system resources. The key idea here is matching capability with responsibility. When delegation is done correctly, the system becomes more efficient, more accurate, and more scalable. Now let's talk about performance and how supervisor worker systems achieve it. As shown on the slide, one of the biggest advantages of this architecture is parallel execution. Multiple worker agents can operate simultaneously. Instead of processing tasks one by one, the system distributes them across multiple workers, dramatically reducing overall execution time. This is especially important for large workloads. As demand increases, you can simply add more workers. The supervisor continues to coordinate tasks without needing to change the core system design. This is what we call horizontal scalability. However, parallel execution introduces new challenges. The system must ensure proper synchronization. Tasks may need to wait for others to complete, or results may need to be combined in a specific order. This is where the supervisor plays a critical role, managing timing, dependencies, and coordination. Now let's look at how the supervisor maintains order across the system. As illustrated on the diagram on the slide, workflow coordination involves several key functions. First, sequencing. The supervisor ensures that tasks are executed in the correct order when dependencies exist. Second, failure handling. If a worker fails or stalls, the supervisor detects the issue and triggers retries automatically. Third, coherence. The supervisor ensures that partial results from different workers are aligned and consistent before moving forward. And finally, aggregation. It combines outputs from multiple workers into a single, unified result. This coordination loop is what keeps the system reliable. Without it, even well-designed agents could produce inconsistent or incomplete results. Now let's talk about how information flows within this architecture. As shown on the slide, communication is bidirectional between the supervisor and workers. When the supervisor assigns a task, it sends a structured payload. This includes the goal, context, constraints, and sometimes deadlines. When the worker completes the task, it returns a structured result. This includes the output, a status indicator, and any error details if something went wrong. This structured communication is critical. It ensures consistency, prevents data loss, and allows the supervisor to process results reliably. Without clear communication contracts, the system can break down due to missing or misinterpreted information. So designing communication formats is just as important as designing the agents themselves. Finally, let's look at how this architecture is used in real-world systems. As shown on the slide, content pipelines are a great example. A supervisor routes a document through multiple workers, planning, writing, and editing, each handling a specific stage. In AI research systems, the supervisor dispatches workers to retrieve, analyze, and synthesize information, often in parallel. Customer support systems use supervisors to route tickets to specialized workers, billing, technical support, or escalation. And in data processing pipelines, tasks like extraction, transformation, validation, and loading are handled by different workers under a central supervisor. In all of these cases, the same pattern applies. A central coordinator, managing a team of specialized workers to achieve complex goals efficiently. Let's wrap up this module by reinforcing the most important ideas behind supervisor-worker architectures. The first key takeaway is control through centralization. The supervisor acts as the control layer of the system. It is responsible for decision-making, task routing, and monitoring. Instead of agents coordinating among themselves, the supervisor ensures that everything flows through a single, structured point. This reduces complexity and makes the system more predictable. The second takeaway is specialization through workers. Worker agents are designed to do one thing well. They focus on specific tasks and operate independently. This eliminates unnecessary complexity and allows each worker to perform at a higher level of efficiency and accuracy. The third takeaway is that delegation enables scale. By breaking down tasks and distributing them across multiple workers, the system can handle much larger workloads. Instead of overloading a single agent, the system spreads work intelligently, making it more scalable and robust. The fourth takeaway is parallel execution drives performance. One of the biggest advantages of this architecture is that multiple workers can operate at the same time. This significantly reduces execution time and allows the system to process large volumes of work efficiently. Concurrency becomes a key performance lever. And finally, the most important concept. Architecture determines reliability. A well-structured system with clear roles, defined communication, and strong coordination will always outperform an unstructured one. Supervisor-worker architecture brings together control, scalability, and efficiency into a single design. As you move forward, remember this. Don't just build agents. Build systems where agents operate under a clear structure, where tasks are delegated intelligently, execution is coordinated, and results are consistently reliable. Because in real-world AI systems, success doesn't come from individual intelligence alone. It comes from well-designed architecture. In this module, we move into one of the most critical components of intelligent systems, memory. Because without memory, AI is fundamentally limited. As introduced on this slide, memory is what transforms AI from a stateless responder into a context-aware agent. A stateless system treats every interaction as completely new. It has no awareness of past conversations, no understanding of user preferences, and no ability to learn over time. This makes it reactive, but not intelligent. Memory changes that. It allows systems to retain information, build context, and evolve their behavior based on past interactions. This is why memory is often described as the architecture of intelligence. It's not just an add-on feature. It's a foundational layer that enables real-world capability. And throughout this module, we'll explore how memory works, how to design it, and how to integrate it into AI systems effectively. Let's now understand why memory is so important. As shown on the slide, memory enables context-aware behavior. Instead of responding only to the current input, the system can consider the entire conversation history. This leads to more relevant and accurate responses. Memory also enables personalization. By remembering user preferences, past interactions, and behavior patterns, the system can tailor its responses to individual users. Another key benefit is multi-step reasoning. In complex tasks, agents must maintain coherence across multiple steps. Memory allows them to track progress, retain intermediate results, and stay aligned with the goal. And finally, memory eliminates repetition. Without memory, systems often repeat the same outputs or lose track of what has already been done. Memory ensures continuity and efficiency. These capabilities are what elevate AI from a simple tool to a truly intelligent system. Now let's look at how memory is structured within an AI system. As illustrated in the diagram on the slide, memory typically exists in 3 layers: short-term, long-term, and persistent. Short-term memory is the active context window. It holds the current conversation and is used for immediate reasoning. Long-term memory stores learned information, such as user preferences, history, and accumulated knowledge. And persistent memory is external storage. This is where data is stored beyond a single session, often in databases or vector stores. Each layer serves a different purpose. Together, they create a system that can think in the moment, remember over time, and scale across interactions. This layered architecture is what enables modern AI systems to operate effectively in real-world scenarios. Let's start with short-term memory. As shown on the slide, short-term memory is the context window. It holds the active prompt and recent conversation history. This is what the model uses to generate responses in real time. Short-term memory is session-bound. It exists only during the current interaction and is cleared once the session ends. It is also responsible for immediate reasoning. Every decision the agent makes is based on what is currently available in this context window. This makes it fast and efficient, but also limited. And those limitations are what lead us to the next concept. Now let's look at where short-term memory breaks down. As highlighted on the slide, the first limitation is the token ceiling. Context windows have a fixed size. As more information is added, older data is pushed out or truncated. This leads to the second issue, vanishing context. Important details from earlier in the conversation may be lost, reducing the system's ability to maintain coherence. And the third limitation is session amnesia. Once the session ends, all information is lost. The system has no memory of past interactions. These limitations make short-term memory insufficient for building intelligent, long-running systems. And this is exactly why we need long-term and persistent memory. Now let's move beyond short-term limitations and explore long-term memory. As shown on the slide, long-term memory is persistent across sessions. Unlike short-term memory, it does not disappear when the interaction ends. Instead, it allows the system to retain knowledge over time. This includes user preferences, past interactions, decisions, and domain-specific knowledge. This is what enables learning and adaptation. The system is no longer starting from zero. It is building on past experience. Another important aspect is recall on demand. Long-term memory is not always active. Instead, relevant information is retrieved when needed and injected into the agent's context. This makes the system both efficient and scalable. In essence, long-term memory transforms AI from reactive to adaptive. Now let's understand the relationship between context windows and persistent memory. As illustrated in the diagram on the slide, these are two separate systems that must work together. The context window is like a working desk. It holds the immediate information the agent needs to think and act. Persistent memory, on the other hand, is like a filing cabinet. It stores large amounts of information externally, beyond the limits of the context window. Neither is sufficient on its own. The context window is fast, but limited. Persistent memory is scalable, but requires retrieval. The key is integration. As highlighted on the slide, the best systems dynamically retrieve relevant information from persistent memory and inject it into the context window at the right time. This creates a seamless bridge between short-term and long-term thinking. Now let's talk about retrieval, arguably the most important part of memory systems. As shown on the slide, storing memory is only half the problem. The real challenge is retrieving the right information at the right time. This process involves several steps. First, query formation. The system must translate the current context into a meaningful search query. Next, semantic search. Instead of relying on exact keyword matches, modern systems use vector embeddings to retrieve information based on meaning. Then comes relevance ranking. Not all retrieved information is equally useful. The system must prioritize the most relevant results. And finally, injection. The selected memory is added back into the prompt, allowing the agent to use it in reasoning. Retrieval quality directly impacts system performance. Good retrieval leads to intelligent behavior. Poor retrieval leads to confusion and errors. Now let's look at how to design memory systems effectively. As shown on the slide, one of the most important decisions is what to store. You should store valuable information, such as user preferences, task history, domain knowledge, and structured metadata. At the same time, you must decide what to discard. Redundant data, outdated information, and low-confidence outputs should be removed. Otherwise, they degrade retrieval quality. Another key consideration is balancing speed and accuracy. Fast retrieval methods may sacrifice precision, while highly accurate methods may increase latency. Designing memory systems is about finding the right balance. The goal is not to store everything. It's to store the right things and retrieve them efficiently. Finally, let's look at how ClawdDB fits into this architecture. As shown on the slide, ClawdDB acts as the memory layer for AI systems. It stores embeddings, vector representations of knowledge, conversations, and context. This enables fast semantic retrieval, allowing agents to query memory in real time. ClawdDB also integrates directly into workflows. At each step of reasoning, relevant memory can be retrieved and injected automatically. This makes the system context-aware without requiring manual intervention. And importantly, it is scalable. As your data grows, ClawDB continues to handle storage and retrieval efficiently. This makes it suitable for both prototypes and production systems. In summary, ClawDB provides the infrastructure needed to turn memory into a functional, scalable component of your AI system. Let's wrap up this module by reinforcing the most important ideas about memory in AI systems. The first and most important takeaway is this: memory equals intelligence. Without memory, AI systems are reactive. They respond to inputs, but they do not learn, adapt, or improve. With memory, they become context-aware, personalized, and capable of handling complex, multi-step tasks. The second takeaway is the distinction between short-term and long-term memory. Short-term memory is the context window. It is fast, temporary, and used for immediate reasoning. But it is limited. It has size constraints and does not persist beyond a session. Long-term memory, on the other hand, is persistent. It stores knowledge, history, and preferences across sessions, allowing the system to build continuity over time. The third takeaway is the importance of persistent memory. As shown earlier in the module, persistent memory acts as external storage, often in the form of databases or vector stores. This is what enables scalability and long-term learning in real-world systems. The fourth takeaway is that retrieval matters more than storage. Storing data is relatively easy. The real challenge is retrieving the right information at the right time. Poor retrieval leads to irrelevant context, which can degrade performance. Strong retrieval strategies, especially semantic search, are what make memory systems effective. And finally, the most important perspective. Memory is the backbone of modern AI systems. No serious AI system today operates without a well-designed memory layer. As you move forward, remember this: don't just build agents that respond. Build agents that remember, learn, and adapt. Because the difference between a basic AI system and an intelligent one is memory. In this module, we transition from understanding memory to understanding how memory becomes actionable intelligence. Because in modern AI systems, simply storing information is not enough. As introduced on this slide, retrieval systems are the mechanism that transforms stored memory into usable knowledge. Think about it this way. An AI system may have access to massive amounts of stored data, documents, embeddings, user history, logs. But none of that matters if it cannot find the right information at the right time. Without retrieval, memory is passive. It exists, but it is not used effectively. Retrieval changes that. It enables the system to actively search through stored knowledge, identify what is relevant, and bring it into the reasoning process. This is why retrieval is often described as the bridge between memory and intelligence. It allows agents to move from knowing everything in theory to using the right knowledge in practice. And in this module, we'll explore how retrieval systems work, from vector search to embeddings to context injection, and how they power modern AI architectures. Now let's understand why retrieval is such a critical component. As shown on the slide, memory alone does not equal intelligence. You can store millions of documents, embeddings, or interaction histories, but that data is essentially inert until it is retrieved and used. Retrieval is what activates memory. It takes stored information and transforms it into context that the model can use during inference. This involves several steps. First, searching the memory store using semantic understanding, then ranking the results based on relevance, and finally, selecting the most useful pieces of information. This process ensures that the agent is not overwhelmed with irrelevant data. Instead, it is guided by high-quality, targeted context. This is what enables grounded responses. Rather than relying purely on its internal training, the model can reference external knowledge dynamically. This makes the system more accurate, more up-to-date, and more aligned with real-world data. Without retrieval, even the most advanced models would struggle to leverage external knowledge effectively. Now let's look at the core challenge that retrieval solves. As highlighted on the slide, modern AI systems deal with extremely large memory stores. These can include millions or even billions of embeddings. But there's a problem. You cannot feed all of this information into the model. Even with large context windows, like 128K tokens, there is still a limit to how much information can be processed at once. This creates a fundamental bottleneck. There is far more information available than can be used at any given time. And this leads to two risks. If you include too much data, the model becomes overwhelmed and loses focus. If you include too little, the model lacks context and produces incomplete or incorrect results. This is why selective retrieval is essential. The system must identify and extract only the most relevant pieces of information. This ensures that the model receives high-quality, focused context without exceeding its limits. In other words, retrieval is about precision, not volume. Now let's dive into the core technology behind retrieval: vector search. As shown on the slide, the key concept here is embeddings. Embeddings are numerical representations of text that capture semantic meaning. Instead of matching exact keywords, embeddings allow the system to understand the meaning behind the text. For example, two sentences that are phrased differently but convey the same idea will have similar embeddings. This is what enables semantic search. When a query is received, it is converted into an embedding vector. This vector is then compared to stored embeddings using similarity metrics, most commonly cosine similarity. The system identifies the closest matches. These are the pieces of information most relevant to the query. This approach is powerful because it goes beyond keyword matching. It allows the system to understand intent, context, and meaning. And this is what makes vector search the foundation of modern retrieval systems. Now let's look at how vector databases enable this process at scale. As shown on the slide, vector databases store embeddings rather than raw text. These embeddings are indexed using specialized data structures designed for fast similarity search. One common approach is approximate nearest neighbor indexing. This allows the system to quickly find vectors that are close to the query vector, even in very large data sets. When a query is made, it follows a clear flow. First, the query is converted into an embedding. Then, the database searches for the nearest neighbors, those embeddings that are most similar. Finally, the top results are returned, ranked by similarity. These results are then used as context for the model. What makes vector databases powerful is their ability to perform this process in milliseconds, even at massive scale. This is what enables real-time retrieval in production AI systems. Without this infrastructure, retrieval would be too slow and inefficient to be practical. Now let's move beyond retrieval concepts and look at how embeddings are actually created and stored. As shown on the slide, embedding pipelines follow a structured flow: ingest, chunk, embed, and store. First, ingestion. This is where raw data enters the system. Documents, PDFs, conversations, or any form of text data. Next comes chunking. Large documents are broken into smaller pieces. This is critical because embeddings work best when they represent focused, meaningful chunks of information rather than entire documents. Then comes embedding. Each chunk is converted into a vector representation using an embedding model. This is what allows the system to perform semantic search later. Finally, storage. These embeddings are stored in a vector database along with metadata, such as source, timestamp, or document type. One key point highlighted on the slide is consistency. The same embedding model must be used during both ingestion and query time. If different models are used, the vector representations will not align, and similarity search will break down. So embedding pipelines are not just about creating vectors, they are about maintaining consistency across the entire system. Now let's look at how a query moves through the retrieval system. As illustrated on the diagram on the slide, the process consists of 4 main steps. First, embedding the query. When a user asks a question, that input is converted into an embedding using the same model used during ingestion. Second, searching the vector database. The system performs an approximate nearest neighbor search to find the most similar vectors. Third, ranking and filtering. The retrieved results are not used directly. They are filtered using metadata and often re-ranked to improve relevance. And finally, preparing context. The top results are selected and formatted into a structure that can be injected into the prompt. This flow is what enables efficient and accurate retrieval. It ensures that the system not only finds relevant information, but also prepares it in a way that the model can use effectively. Now we reach the final step, context injection. As shown on the slide, retrieved memory is not used as is. It must be carefully structured before being passed to the model. The typical prompt structure includes 3 components. First, the system prompt. This defines the agent's role and behavior. Second, the retrieved memory. These are the relevant chunks retrieved from the database. And third, the user query. These elements are combined into a single structured prompt. But there's an important challenge here: context overload. If too much information is injected, the model becomes less effective. It may lose focus or produce degraded outputs. That's why prioritization is critical. Only the most relevant chunks should be included. Additionally, structure matters. Using clear delimiters, labels, and formatting ensures that the model can interpret the context correctly. Context injection is not just about adding information, it's about adding the right information in the right way. Now let's step back and look at system design. As shown on the slide, building an effective retrieval system involves several key trade-offs. First, chunk size. Smaller chunks improve precision because they contain focused information. Larger chunks provide more context but may introduce noise. Second, re-ranking. After initial retrieval, additional models, such as cross-encoders, can be used to improve the ranking of results. Third, metadata filtering. By filtering results based on attributes like date, source, or entity, you can narrow down the search space and improve relevance. And finally, recall versus precision. Retrieving more results increases the chance of finding relevant information, but may introduce noise. Retrieving fewer results improves precision, but risks missing useful data. Designing retrieval systems is about balancing these trade-offs. There is no one-size-fits-all solution. It depends on your use case. Finally, let's look at how retrieval integrates into agent workflows. As shown on the slide, retrieval is not a one-time step. In modern systems, agents perform retrieval at each reasoning step. This is called step-level retrieval. Instead of retrieving information only at the beginning, the agent continuously updates its context as it progresses through a task. This enables dynamic context injection. As the agent's state evolves, new information is retrieved and injected into the prompt. Another important concept is feedback loops. New observations and results can be written back into memory, allowing the system to learn and improve over time. And finally, real-time support. Retrieval allows agents to access up-to-date information without retraining the model. This is what makes modern AI systems both flexible and scalable. Retrieval turns static models into dynamic systems, capable of adapting to new information in real time. Let's wrap up this module by reinforcing the most important ideas about retrieval and context injection. The first and most critical takeaway is this: retrieval is the bridge between memory and reasoning. As highlighted on the slide, without retrieval, stored knowledge is effectively inaccessible at inference time. You may have massive amounts of data, documents, embeddings, logs, but unless you can retrieve the right pieces at the right moment, that knowledge cannot be used. Retrieval is what activates memory. It transforms static storage into dynamic intelligence. The second takeaway is the power of vector search and embeddings. Traditional systems rely on keyword matching, which often fails to capture meaning. Vector search, on the other hand, enables semantic understanding. By converting text into embeddings, the system can find information based on meaning, not just exact matches. This allows AI systems to retrieve relevant context even when the wording is different. And this is what makes modern retrieval systems so powerful. The third takeaway is that pipeline consistency is non-negotiable. As emphasized in the module, the same embedding model must be used during both ingestion and query time. If there is a mismatch, the vectors will not align properly, and retrieval quality will degrade significantly. This is one of the most common pitfalls in building retrieval systems. So consistency is not just a best practice, it's a requirement. The fourth takeaway is that retrieval quality determines system performance. Even the most powerful language model cannot compensate for poor retrieval. If irrelevant or low-quality information is injected into the prompt, the model will produce poor outputs. This is often summarized as garbage in, garbage out. High-quality retrieval leads to accurate, grounded responses. Low-quality retrieval leads to confusion and errors. And finally, the most important design principle: retrieval is not an afterthought, it is core infrastructure. As shown on the slide, retrieval systems are not optional add-ons. They are foundational to how modern AI systems operate. From RAG systems to multi-agent architectures, retrieval is what enables agents to access external knowledge dynamically. So as you move forward, remember this: don't just focus on storing data. Focus on how that data will be retrieved, ranked, and injected into the system. Because the true power of AI systems does not come from how much they know. It comes from how effectively they can use that knowledge at the right time. And that is what retrieval enables. In this module, we move from intelligence to action, because thinking alone is not enough. As introduced on this slide, the execution layer is what transforms AI systems from reasoning engines into systems that can actually do things in the real world. Language models are incredibly powerful at generating text, planning, and decision-making, but they cannot execute actions on their own. They cannot call APIs, send emails, query databases, or trigger workflows unless we give them that capability. And that capability comes from the execution layer. It acts as the bridge between thinking and doing. The model decides what needs to be done, and the execution layer makes it happen. This is where AI systems move beyond conversation and into real-world impact. To understand the execution layer more clearly, we can break it down into 3 stages, as illustrated on the slide: thinking, calling, and doing. First, the thinking stage is where the model processes the input, understands the goal, and determines the appropriate action. This is the reasoning phase where the agent decides what needs to happen. Next is the calling stage, where the model selects a tool and generates a structured function call that describes the action to be performed. Importantly, the model does not execute the action itself, it only describes it. Finally, we have the doing stage, where the tool executes the action in the real world. This could involve calling an API, retrieving data, running code, or interacting with external systems. The result is then returned back to the model, updating its context. This separation between decision-making and execution is critical because it ensures safety, control, and reliability. It allows us to build systems where the model focuses on reasoning, while the execution layer handles real-world interactions in a controlled and predictable way. Tool calling is one of the most important capabilities in modern AI systems because it enables models to move beyond text and into action. As highlighted on the slide, language models are excellent at reasoning, but they cannot act on their own. Their outputs are limited to text, which means they can only suggest actions rather than perform them. Tools solve this limitation by connecting the model to external systems such as APIs, databases, and services. This allows the system to actually execute tasks instead of just describing them. For example, instead of telling a user how to retrieve data, the system can directly fetch the data itself. This is what makes AI systems truly useful in real-world applications. Tool calling is also the foundation of autonomous agents. It enables systems to operate independently, make decisions, and carry out actions without constant human intervention. Without tool calling, AI remains a conversational interface. With it, AI becomes an operational system capable of driving real outcomes. Now let's explore how we convert real-world actions into tools that AI systems can use. As shown on the slide, any action can be abstracted into a callable function. This means we take a task and wrap it in a structured interface that the model can invoke. For example, fetching data from a database becomes a tool that accepts query parameters and returns results. Sending an email becomes a function that takes a recipient, subject, and message as inputs. Running computations becomes a tool that executes code and returns outputs. The key idea here is abstraction. By representing actions as tools, we create a standardized way for the model to interact with the real world. This makes the system modular and flexible. Each tool represents a specific capability, and the model can dynamically decide which tool to use based on the context. This approach also makes systems easier to scale, as new tools can be added without changing the core logic of the model. In essence, tools turn capabilities into reusable building blocks. Finally, let's look at how to design tools effectively for reliable execution. As shown on the slide, there are 4 key principles that every tool should follow. First, clear input and output definitions are essential. Every tool should have well-defined parameters and structured outputs, ensuring that there is no ambiguity in how it is used. Second, each tool should have a single responsibility. Instead of building complex tools that try to do everything, it is better to design focused tools that perform one task well. This improves composability and makes it easier to build workflows. Third, tools should exhibit deterministic behavior. Given the same input, they should produce the same output. This ensures predictability and reliability in execution. And fourth, tools must include robust error handling. When something goes wrong, the tool should return structured error messages rather than failing silently. This allows the system to detect issues and apply retry or fallback strategies. Together, these principles ensure that tools are predictable, composable, and safe, making them suitable for production-grade AI systems. Now let's move deeper into how tools are actually used, starting with structured inputs. As shown on the slide, one of the most important aspects of tool execution is defining inputs explicitly. Instead of relying on natural language instructions, tools operate using structured formats, typically JSON or schema-based inputs. This means every parameter is clearly defined, typed, and validated before execution. For example, instead of saying "get weather for New York," a structured input would specify fields like city, date, and units. This eliminates ambiguity and ensures that the tool behaves consistently every time it is called. Structured inputs also make systems more reliable because they remove guesswork. The model does not need to interpret vague instructions. It simply fills in predefined fields. This leads to deterministic execution, where the same input always produces the same outcome. Additionally, schema-based validation ensures that invalid inputs are caught early, preventing downstream errors. In production systems, this level of structure is essential because it enables safe, predictable, and scalable execution across multiple tools and workflows. Just as inputs must be structured, outputs are equally important. As highlighted on the slide, a well-designed tool should return structured outputs that the model can easily interpret and use. Typically, outputs include three key components: status, results, and errors. The status indicates whether the execution was successful, failed, or partially completed. The results contain the actual data returned by the tool, formatted in a structured way such as JSON. And errors provide detailed information when something goes wrong. This structure is critical because it allows the system to reason about the outcome of each action. For example, if a tool fails, the system can detect the error and trigger a retry or fallback mechanism. Structured outputs also enable chaining between tools. The output of one tool can become the input of another, creating multi-step workflows. Without structured outputs, this kind of orchestration would be unreliable and difficult to manage. In essence, outputs are not just results. They are signals that guide the next step in the system's execution process. Now let's look at how function calling actually works in practice. As shown on the slide, function calling follows a loop that connects the model to the execution layer. The process begins with the model analyzing the input and deciding that a tool is needed. It then generates a structured function call, specifying the tool name and the required parameters. Importantly, the model does not execute the tool, it only describes the call. The runtime system receives this function call, executes the tool, and returns the result. This result is then injected back into the model's context, allowing it to continue reasoning. This loop can repeat multiple times as the system works toward completing a task. This architecture is powerful because it separates reasoning from execution. The model focuses on decision-making, while the runtime handles real-world interactions. This ensures safety, control, and flexibility. It also allows developers to monitor and manage tool execution independently of the model itself. As systems become more complex, different patterns of function calling emerge. As shown on the slide, the simplest pattern is single execution, where one tool is called to perform a specific task and return a result. This works well for straightforward use cases. However, more complex tasks often require multi-step chains, where the output of one tool feeds into another. For example, a system might first fetch data, then process it, and finally send a report. Another important pattern is dynamic tool selection. Instead of hard-coding which tool to use, the model chooses the appropriate tool based on context. This makes the system more flexible and adaptive. Finally, we have retry and fallback mechanisms. In real-world systems, failures are inevitable, so the system must be able to recover gracefully. This could involve retrying a failed call, switching to an alternative tool, or adjusting the parameters. These patterns are what enable robust, production-ready AI systems. Finally, let's bring everything together with orchestration. As shown on the slide, tool orchestration is the layer that manages multiple tools and integrates them into a cohesive workflow. Instead of tools operating independently, the orchestration layer ensures that tasks are routed correctly, dependencies are resolved, and execution flows smoothly. For example, a system might use a data fetching tool to retrieve information, then pass that data to a processing tool, and finally use another tool to deliver the output. The orchestration layer coordinates all of this. It determines which tool to call, when to call it, and how to handle the results. It also integrates tool execution into the agent's reasoning loop, ensuring that decisions and actions remain aligned. This is what enables complex, multi-step workflows to operate reliably. Without orchestration, systems would be fragmented and difficult to manage. With it, they become structured, scalable, and capable of handling real-world complexity. This is where AI systems truly become operational. Let's wrap up this module by reinforcing the most important ideas about the execution layer and tool calling. The first key takeaway is this: tools enable execution. Language models are powerful at reasoning, planning, and generating text, but they cannot take real-world actions on their own. Tools are what bridge that gap. They allow AI systems to interact with external environments, APIs, databases, services, and actually perform tasks. This is what transforms AI from a conversational system into an operational one. The second takeaway is the importance of structure. As we saw throughout this module, structured inputs and outputs are critical for reliable execution. Inputs must be explicitly defined using schemas, ensuring that the model provides all required parameters in a consistent format. Outputs must also be structured, containing clear status indicators, results, and error messages. This structure eliminates ambiguity, improves reliability, and enables chaining across multiple tools. The third takeaway is that function calling powers modern agents. The model does not directly execute actions. It generates structured function calls. The runtime system then executes those calls and returns the results. This separation between reasoning and execution is what makes the system safe, controllable, and scalable. It allows developers to monitor and manage execution independently of the model's decision-making process. The fourth takeaway is orchestration. As systems grow more complex, multiple tools must work together in coordinated workflows. Orchestration ensures that tasks are routed correctly, dependencies are resolved, and execution flows smoothly. It enables multi-step processes where outputs from one tool feed into another, creating powerful end-to-end systems. And finally, the most important insight. The execution layer is what separates demos from real systems. Without it, AI remains limited to generating suggestions. With it, AI becomes capable of taking action, solving real problems, and integrating into real-world workflows. So as you move forward, remember this: don't just design agents that think, design systems that act. Because the true value of AI is not in what it can say, it's in what it can do. In this module, we take the next major step in building real-world AI systems, moving from individual tool execution to full workflow automation. Up to this point, we've learned how agents think, retrieve information, and execute actions using tools. But real-world systems are not built on isolated actions. They are built on sequences of actions that work together as a pipeline. As introduced on this slide, workflow automation is the process of connecting these steps into a structured flow that can execute end-to-end without manual intervention. Instead of triggering one tool at a time, we design systems where tasks automatically pass from one stage to the next. This creates continuity, reduces friction, and enables the system to operate independently. In production environments, this is essential. Whether it's processing data, generating content, or handling customer workflows, automation ensures that the system can handle tasks reliably and repeatedly. This is the foundation of scalable AI systems. You are no longer building tools. You are building systems that run continuously, adapt to inputs, and deliver outputs without constant human oversight. Now let's understand why workflow automation is so important in modern AI systems. As highlighted on the slide, there are three key benefits: speed, accuracy, and scale. First, speed. Automated systems execute tasks instantly without waiting for human input between steps. This eliminates delays and allows workflows to complete much faster than manual processes. Second, accuracy. Human-driven workflows are prone to errors, especially when tasks are repetitive or complex. Automation ensures that each step is executed consistently, reducing variability and improving reliability. And third, scale. Perhaps the most important benefit is the ability to handle large volumes of work without additional effort. Once a workflow is automated, it can process thousands or even millions of tasks with the same efficiency as one. As shown on the slide, this is what allows AI systems to operate at production scale. Automation is not just a convenience, it is a necessity for building systems that are fast, reliable, and capable of handling real-world workloads. Without it, AI remains limited to small-scale or manual operations. At the core of workflow automation is the concept of tool chaining. As illustrated on the slide, tool chaining means that the output of one tool becomes the input of the next, creating a continuous flow of execution. This is the fundamental building block of every automation system. Instead of treating each tool as an isolated function, we connect them into a sequence where each step contributes to the final outcome. For example, a system might start by fetching data from an API, then pass that data to another tool for processing, and finally use a third tool to generate a report. Each step depends on the previous one, forming a chain of execution. As emphasized on the slide, tool chaining is what makes complex workflows possible. It allows us to break down large tasks into smaller, manageable steps while maintaining a coherent flow. When designed correctly, chaining enables modularity, where each tool can be reused across different workflows. This is what makes automation systems flexible, scalable, and efficient. Not all workflows follow the same pattern, which is why understanding different types of tool chains is important. As shown on the slide, there are four main types: linear, conditional, parallel, and hybrid. Linear chains are the simplest. They execute tasks step by step in a fixed order. This works well for straightforward workflows, where each step depends on the previous one. Conditional chains introduce decision-making into the workflow. Based on certain conditions, the system can branch into different paths, allowing for more dynamic behavior. Parallel chains allow multiple tools to run simultaneously, improving performance and reducing execution time. This is especially useful when tasks are independent and do not rely on each other. Finally, hybrid workflows combine all these patterns into a more flexible system. They allow for complex execution flows that adapt to different scenarios. Choosing the right chain type depends on the nature of the task and the level of complexity required. Understanding these patterns is key to designing efficient and scalable automation systems. Now, let's bring everything together and look at how to build automation pipelines. As shown on the slide, this process follows a structured blueprint with 4 key steps: define, stage, assign, and validate. First, define the workflow. This involves clearly mapping out the start, process, and output states. You need to understand what the system is trying to achieve and how the data flows through it. Second, stage the workflow. Break the process into discrete, manageable steps that can be executed independently. Third, assign tools. Each stage is mapped to a specific tool that performs the required action. This ensures that responsibilities are clearly defined and execution is consistent. And finally, validate the pipeline. This step ensures that data flows correctly between stages and that each tool produces the expected output. Validation is critical for reliability, especially in production systems. By following this structured approach, you can design pipelines that are robust, scalable, and easy to maintain. This is what transforms a collection of tools into a fully functional automation system. Now that we understand pipelines, let's talk about what keeps them running smoothly: workflow orchestration. As shown on the slide, orchestration is the layer responsible for managing execution across all stages of the pipeline. It ensures that each step runs at the right time, in the correct order, and with the required dependencies satisfied. One of the key responsibilities of orchestration is dependency management. Certain tasks cannot begin until others are completed, and the system must enforce these relationships to maintain correctness. Another critical function is execution control. The orchestration layer determines the sequencing and prioritization of tasks, ensuring that workflows progress logically and efficiently. Additionally, orchestration provides visibility into the system. It allows us to monitor progress, detect bottlenecks, and understand where delays or failures occur. Without orchestration, even well-designed pipelines can become unreliable and difficult to manage. With it, workflows become structured, predictable, and scalable. This is what enables complex systems to operate consistently in real-world environments. In real-world systems, failures are inevitable. That's why handling failures gracefully is a critical part of workflow design. As highlighted on the slide, there are several strategies to ensure reliability. First, retry logic. When a task fails due to temporary issues, such as network errors, the system should automatically retry the operation, often with exponential backoff, to avoid overwhelming the system. Second, fallback mechanisms. If the primary tool fails, the system can switch to an alternative tool or approach to complete the task. This ensures continuity even when components fail. Third, logging. Every step in the pipeline should be logged, creating a detailed trace of execution. This is essential for debugging and understanding what went wrong. And finally, reliability by design. Instead of building systems that break completely on failure, we design systems that degrade gracefully. This means partial results can still be produced, and workflows can recover without complete failure. These strategies ensure that automation systems are robust and dependable, even under imperfect conditions. In real-world systems, failures are inevitable. That's why handling failures gracefully is a critical part of workflow design. As highlighted on the slide, there are several strategies to ensure reliability. First, retry logic. When a task fails due to temporary issues, such as network errors, the system should automatically retry the operation, often with exponential backoff to avoid overwhelming the system. Second, fallback mechanisms. If the primary tool fails, the system can switch to an alternative tool or approach to complete the task. This ensures continuity even when components fail. Third, logging. Every step in the pipeline should be logged, creating a detailed trace of execution. This is essential for debugging and understanding what went wrong. And finally, reliability by design. Instead of building systems that break completely on failure, we design systems that degrade gracefully. This means partial results can still be produced and workflows can recover without complete failure. These strategies ensure that automation systems are robust and dependable, even under imperfect conditions. As systems grow, scalability becomes a key concern. As highlighted on the slide, designing scalable workflows requires a few important principles. First, modular design. Each stage of the pipeline should be self-contained and independent, allowing it to be reused or modified without affecting the entire system. Second, reusable tools. Instead of building new tools for every workflow, we create general-purpose tools that can be used across multiple pipelines. This reduces development effort and increases consistency. Third, parallel execution. By running independent tasks simultaneously, we can significantly improve performance and reduce latency. And finally, continuous monitoring. Scalable systems require visibility. By tracking performance metrics and analyzing system behavior, we can identify bottlenecks and optimize workflows over time. Scalability is not just about handling more tasks. It's about maintaining performance and reliability as the system grows. These principles ensure that workflows remain efficient and adaptable, even at large scale. Let's now step back and look at the bigger picture. As shown on the slide, workflow automation is what transforms individual tools into complete systems. A single tool can perform a task, but a workflow connects multiple tools into a cohesive process that delivers end-to-end results. This is the difference between a feature and a system. When tools are chained together, orchestrated effectively, and designed for reliability, they become part of a larger architecture that can operate independently. This is what defines production-grade AI systems. They are not just collections of capabilities. They are integrated systems that solve real problems. Workflow automation is the layer that brings everything together. It ensures that reasoning, retrieval, execution, and memory all work in harmony. And this is what ultimately enables AI to move from experimentation to real-world deployment. In this module, we move from back-end systems and execution layers to the point where users actually interact with AI, interfaces. Because no matter how powerful your system is, it only becomes valuable when users can access it effectively. As introduced on the slide, AI interfaces act as the bridge between humans and intelligent systems. They translate user intent into machine-understandable input, and then convert machine outputs into meaningful responses. This translation layer is critical. AI systems are inherently complex and probabilistic, but interfaces must feel simple, intuitive, and reliable. This creates a design challenge. How do we make advanced systems feel effortless to use? The answer lies in thoughtful interface design. Whether it's a chat interface, an API, or a dashboard, the goal is always the same: reduce friction and maximize usability. A well-designed interface hides complexity while exposing capability. It ensures that users can interact with AI naturally without needing to understand the underlying system. And this is what ultimately determines whether an AI system succeeds or fails in the real world. Now, let's explore the different types of AI interfaces. As shown on the slide, there are multiple ways users and systems can interact with AI, each serving a different purpose. The most common is chat-based interfaces, where users interact using natural language. These are intuitive and accessible, making them ideal for non-technical users. Next are API-based interfaces, which provide programmatic access to AI capabilities. These are designed for developers and allow AI to be integrated into applications and systems. Then we have UI dashboards, which present AI insights and controls through visual interfaces. These are often used in enterprise environments where users need to monitor and manage AI outputs. Finally, there are voice and multimodal interfaces, which combine text, speech, images, and other inputs to create richer interaction experiences. Each interface type serves a different audience, from end users to developers to enterprise systems. Understanding these types allows you to design the right interface for your use case, ensuring that the system is both usable and effective. Let's now focus on chat-based interfaces, which are one of the most popular forms of AI interaction. As highlighted on the slide, chat interfaces are built around conversational models, where users interact using natural language. This makes them highly intuitive, as users can simply type or speak their requests without needing to learn a new system. Another key feature is context awareness. Chat-based systems maintain conversation history, allowing them to provide coherent and relevant responses across multiple turns. This creates a more natural and engaging experience. As shown on the slide, real-world examples include chatbots, AI assistants, customer support systems, and coding co-pilots. These interfaces are powerful because they lower the barrier to entry. Anyone can use them, regardless of technical expertise. However, designing effective chat interfaces requires careful attention to detail. You must ensure that responses are clear, helpful, and aligned with user intent. This is where design principles come into play. Designing great chat experiences is not just about connecting a model. It's about guiding user interaction effectively. As shown on the slide, there are 4 key principles. First, writing clear prompts. Interfaces should guide users with examples, placeholders, or suggested actions, helping them understand what they can do. Second, preserving context. The system should remember previous interactions so users don't have to repeat themselves. This improves usability and creates a seamless experience. Third, handling ambiguity gracefully. Instead of failing when the input is unclear, the system should ask clarifying questions. This keeps the interaction smooth and user-friendly. And fourth, surfacing feedback. This includes showing loading states, error messages, and confidence indicators. These signals build trust and help users understand what the system is doing. As emphasized in the slide, great chat design is about making AI feel reliable, transparent, and easy to use, even when the underlying system is complex. Finally, let's look at API-based systems, which are the backbone of scalable AI applications. As shown on the slide, APIs expose AI capabilities in a structured, programmatic way. Instead of interacting through a user interface, developers can send requests to an API and receive responses. This allows AI to be integrated into web apps, mobile apps, back-end systems, and enterprise platforms. The typical flow is straightforward. A request is sent to the API, the system processes it using models and business logic, and a structured response is returned. Technologies like REST and GraphQL are commonly used to implement these systems. The key advantage of APIs is decoupling. The front end and back end are separated, allowing each to evolve independently. This makes systems more flexible and scalable. As highlighted in the slide, APIs are what enable AI to move beyond standalone tools and become part of larger ecosystems. They are the foundation for building integrated, production-ready AI systems. Now let's look at how everything connects in a real system, linking the front-end interface to the underlying AI agent. As shown on the slide, this process typically follows 3 steps. First, user input. The front end, whether it's a web app, mobile app, or chat interface, captures the user's intent and converts it into a structured request. This could be a simple text input or a more complex payload, depending on the application. Second, agent processing. The backend receives this request and routes it to the appropriate agent. The agent then performs its work. This may involve reasoning with a language model, retrieving memory, or calling external tools. And finally, response delivery. The result generated by the agent is formatted into a user-friendly response and sent back to the front end. This flow is what enables seamless interaction between users and AI systems. It abstracts away the complexity of the backend while delivering meaningful outputs to the user. Designing this connection properly is critical for performance, reliability, and user experience. Now let's dive deeper into the backend architecture that powers AI interfaces. As illustrated in the diagram on the slide, most systems are built around three core layers: the API layer, the agent layer, and the execution layer, along with observability across all of them. The API layer is responsible for handling incoming requests. It manages routing, authentication, and rate limiting, ensuring that the system can scale and remain secure. The agent layer is where intelligence lives. This is where the system orchestrates language model calls, retrieves memory, and decides which tools to use. Below that is the execution layer, which actually performs actions such as calling APIs, querying databases, or running code. And finally, observability ties everything together. It provides logging, monitoring, and performance tracking, allowing developers to understand how the system behaves in real time. This layered architecture is what makes modern AI systems scalable, maintainable, and production-ready. Each layer has a clear responsibility, and together they form a cohesive system. User experience is heavily influenced by how quickly and smoothly the system responds, which is why real-time interaction patterns are so important. As shown on the slide, one of the most effective techniques is streaming responses. Instead of waiting for the full response to be generated, the system sends tokens as they are produced. This reduces perceived latency and makes the system feel faster. Another important pattern is incremental updates. Rather than delivering results all at once, the system can provide partial outputs progressively. This is especially useful for long-running tasks, as it keeps users engaged and informed. The slide also highlights the difference between synchronous and asynchronous execution. Simple queries can be handled synchronously, where the user waits for a response. More complex tasks may require asynchronous processing, where the system handles the request in the background and returns the result later. These patterns are essential for designing responsive and user-friendly AI interfaces. Now let's look at how AI systems connect to the broader ecosystem. As shown on the slide, real-world AI value comes from integration, not isolation. AI systems need to interact with external data sources, platforms, and workflows to be truly useful. This includes databases, vector stores, and document retrieval systems that provide the data needed for decision-making. It also includes embedding AI into existing platforms such as CRMs, ERPs, developer tools, and SaaS products. Another important concept is event-driven integration. Using webhooks and message queues, AI systems can be triggered automatically when certain events occur, such as a new user request or a system update. This enables automation at scale. Finally, AI agents themselves can act as orchestrators, coordinating multi-step workflows across different systems. These integrations are what transform AI from a standalone feature into a core part of business processes. Let's step back and look at the bigger picture. As shown on the slide, building an interface is not just about connecting inputs and outputs, it's about creating a complete product experience. A successful AI product combines front-end design, back-end architecture, and intelligent agents into a seamless system. The interface is what users see, but it is only one part of the equation. Behind the scenes, APIs, agents, memory systems, and execution layers work together to deliver value. This is what defines full-stack AI development. It's not enough to build a powerful model. You need to design how users interact with it, how it integrates into workflows, and how it scales in production. When all these components come together, you move from building features to building products. And this is where real-world impact happens, when AI becomes part of everyday tools and workflows, delivering consistent, measurable value. Let's wrap up this module by reinforcing the most important ideas about building AI interfaces. The first key takeaway is this: interfaces connect humans to AI systems. As highlighted on the slide, every interface acts as a translation layer between user intent and machine execution. No matter how powerful your backend is, users only experience what the interface exposes. This means the interface is not just a UI, it is a critical part of the system design. A well-designed interface makes complex systems feel simple, intuitive, and usable. The second takeaway is the power of chat-based interfaces. Chat is one of the most accessible forms of interaction. It allows users to communicate with AI using natural language, without needing technical knowledge. This dramatically lowers the barrier to entry. As a result, chat interfaces are widely used in assistance, customer support, and productivity tools. However, their effectiveness depends on thoughtful design, clear prompts, context awareness, and graceful handling of ambiguity. The third takeaway is the importance of API-based systems. APIs are what make AI scalable and integratable. They allow developers to connect AI capabilities to applications, platforms, and services. By decoupling the front end from the back end, APIs enable flexibility and modularity. This is what allows AI to move beyond standalone tools and become part of larger systems. The fourth takeaway is that great AI products require full-stack thinking. As shown in the architecture diagram earlier in the module, successful systems combine front-end interfaces, back-end APIs, agent logic, and execution layers. Each layer plays a role in delivering value. Focusing on only one part, such as the model, limits the system's effectiveness. Real-world impact comes from integrating all components into a cohesive system. And finally, the most important insight: integration unlocks real-world value. AI becomes truly useful when it is embedded into existing workflows and systems. Whether it's connecting to databases, integrating with enterprise tools, or triggering automated processes, integration is what turns AI into a practical solution. Standalone AI features may be impressive, but integrated AI systems drive measurable outcomes. So as you move forward, remember this: don't just build AI models. Design how users interact with them, how systems connect to them, and how they fit into real workflows. Because the success of AI is not just about intelligence, it's about accessibility, usability, and integration. In this module, we move from building AI systems to connecting them with the real world. Because an AI system, no matter how powerful, has limited value if it operates in isolation. As introduced on the slide, external integrations are what transform standalone models into connected ecosystems. They allow AI to interact with APIs, databases, webhooks, and external services, enabling real-world execution and impact. This is a fundamental shift from prediction to action. Instead of just generating responses, AI systems can now fetch live data, trigger workflows, and interact with business systems. As emphasized in the opening of the deck, this is what moves AI from prototypes to production systems. Integrations are not an add-on. They are a core component of real-world AI architecture. They enable systems to operate in dynamic environments, respond to real-time events, and deliver meaningful outcomes. In essence, integrations are what turn intelligence into utility. Now, let's understand why integrations are so critical. As highlighted on the slide, integrations unlock real impact in 4 key ways. First, real-time data access. AI systems can pull live information during execution, whether it's financial data, system metrics, or user activity, ensuring that decisions are based on current information rather than outdated data. Second, business workflow integration. AI can be embedded directly into operational systems such as CRMs, ERPs, and internal tools, allowing it to participate in real business processes. Third, the transition from demo to production. Many AI systems remain prototypes because they lack integration. By connecting to real systems, they become deployable and useful. And finally, increased usefulness. AI that can act by triggering workflows or updating systems is far more valuable than AI that only predicts or suggests. As shown on page 2 of the document, integrations are what move AI from passive intelligence to active systems that deliver measurable value. At the core of most integrations are APIs, which serve as the universal interface for connecting systems. As explained on page 3 of the document, APIs allow AI systems to send requests and receive structured responses from external services. This communication typically follows a request-response model, where the system sends a query and receives data in return. Technologies like REST and GraphQL are commonly used to implement these interactions. APIs are powerful because they decouple systems. The AI does not need to know how the external service works internally. It only needs to know how to communicate with it. This makes integrations flexible and scalable. APIs also standardize communication, allowing different systems to interact seamlessly. Whether it's retrieving user data, calling external services, or triggering actions, APIs are the backbone of integration. Without them, connecting AI to external systems would be complex and inefficient. While APIs are request-driven, webhooks introduce an event-driven approach. As shown on page 4 of the document, webhooks allow systems to react instantly when an event occurs. Instead of constantly polling for updates, the system receives a push notification in the form of an HTTP request when something happens. For example, when a user signs up, a webhook can trigger an AI-driven onboarding process. This creates real-time automation. The sequence is simple. An event occurs, the webhook fires, the AI system is triggered, and an action is executed. This model is highly efficient because it eliminates unnecessary requests and reduces latency. It also enables reactive systems that respond immediately to changes. Webhooks are especially useful in workflows where timing matters, such as notifications, monitoring, and automated processes. Together with APIs, they form the foundation of modern integration architectures. Finally, let's look at the role of data in integrations. As highlighted on page 5 of the document, every AI decision is only as good as the data behind it. This makes databases a critical component of any integrated system. There are 3 main types of databases commonly used. SQL databases store structured, relational data and are ideal for transactional systems. NoSQL databases handle unstructured or high-volume data, offering flexibility and scalability. And vector databases enable semantic search, forming the backbone of retrieval-based systems like RAG. Choosing the right database depends on the use case, as it impacts query speed, scalability, and retrieval quality. Databases are not just storage, they are active participants in the system. They provide the context and information that AI systems need to make decisions. Without reliable and well-structured data sources, even the most advanced AI models cannot perform effectively. Now let's talk about one of the most powerful advantages of external integrations: real-time data usage. As highlighted on page 6 of the document, AI systems become significantly more valuable when they can access live data during execution. Instead of relying on static or preloaded information, the system can pull the latest data at the moment it is needed. This is critical in domains where information changes rapidly. For example, in finance, systems can access live market data, pricing signals, and portfolio updates. In weather-based applications, dynamic forecasts can be used for planning and logistics. In monitoring systems, real-time alerts and anomaly detection ensure timely responses. The key idea is simple. Stale data leads to stale AI. If the system relies on outdated information, its outputs become less accurate and less useful. By streaming live data into workflows, we ensure that the AI remains relevant, responsive, and grounded in reality. This is what enables high-quality decision-making in real-world systems. Now let's explore how integrations are structured in practice. As shown on page 7 of the document, there are several common integration patterns, each with its own trade-offs. The first is the request-response pattern. This is a synchronous model where the system sends a request and waits for a response. It is simple and works well for low-latency queries. The second is event-driven integration. This is asynchronous and reactive, where systems respond to events as they occur, often using webhooks or message queues. This pattern is highly scalable and efficient for real-time workflows. The third is batch processing. In this model, tasks are processed in bulk at scheduled intervals. It is useful for high-volume operations where immediate response is not required. And finally, hybrid systems combine multiple patterns to handle real-world complexity. Choosing the right pattern depends on factors such as latency requirements, scalability needs, and system complexity. Understanding these patterns allows you to design integrations that are both efficient and reliable. As integrations expand system capabilities, they also introduce risks. That's why safe execution patterns are essential. As emphasized on page 8 of the document, every external call represents a trust boundary, and systems must be designed to handle this responsibly. The first principle is input validation. All external inputs must be sanitized and verified before processing. This prevents malicious or malformed data from causing issues. The second principle is rate limiting. By controlling how frequently requests can be made, we protect both our system and external services from abuse or overload. Third is access control. Using scoped credentials and least privilege API keys ensures that systems only have access to what they need, nothing more. And finally, guardrails. These are constraints that prevent harmful or unintended actions, especially in autonomous systems. Together, these practices ensure that integrations remain secure, reliable, and safe to operate in production environments. In real-world systems, external services will fail at some point. That's why reliability and monitoring are critical components of integration design. As highlighted on page 9 of the document, systems must be built with failure in mind. The first step is logging. Every external call should be recorded, including inputs, outputs, and errors. This creates a trace that can be used for debugging. Next is failure handling. Systems should detect when something goes wrong and respond appropriately. This often includes retry mechanisms, such as exponential backoff, to handle temporary failures. Fallback strategies are also important. If one service fails, the system can switch to an alternative or return a safe default response. Finally, observability ties everything together. By tracking metrics such as latency, success rates, and error frequency, we gain visibility into system performance. As the slide emphasizes, you cannot fix what you cannot see. Monitoring is not optional. It is essential for maintaining reliable production-grade systems. Let's step back and look at the bigger picture. As shown across the module, integrations are not just about connecting systems, they are about building ecosystems. When AI systems are connected to APIs, databases, webhooks, and external services, they become part of a larger network of functionality. This is what enables them to operate in real-world environments. Instead of acting in isolation, they participate in workflows, respond to events, and interact with other systems. This is where AI delivers its greatest value, not as a standalone feature, but as an integrated component within a broader system. As emphasized throughout the module, integration is what transforms AI from a capability into a solution. It allows systems to scale, adapt, and deliver measurable impact. And this is the ultimate goal of building AI systems, to create solutions that work seamlessly within real-world environments and drive meaningful outcomes. In this module, we move into one of the most advanced and impactful areas of AI systems, continuous, long-running execution. Because real-world AI is not about one-time responses, it's about systems that run continuously, monitor environments, and act over time. As introduced on the slide, continuous AI systems represent a shift from single interactions to always-on execution. Traditional AI systems respond to a prompt and stop, but continuous systems loop, observe, and act indefinitely. They operate without constant human input, enabling automation at scale. This is where AI transitions from being a tool to becoming an autonomous system. As emphasized in the opening of the document, this is the foundation of production AI engineering. These systems don't just respond, they work continuously in the background, handling workflows, reacting to changes, and driving outcomes over time. This is the future of AI systems. To understand continuous systems more clearly, let's compare them with traditional systems. As shown on page 2 of the document, one-time tasks involve a single prompt and a single response. There is no memory, no continuity, and no persistence. Once the task is complete, the system stops. In contrast, long-running systems operate continuously. They loop, monitor, and act over extended periods of time, sometimes indefinitely. These systems maintain awareness of their environment and respond to changes as they occur. Another important distinction highlighted on the slide is between autonomous and triggered systems. Autonomous systems act independently, making decisions based on internal logic and continuous observation. Triggered systems, on the other hand, respond to specific events, such as incoming data or user actions. Both approaches are important, and in many real-world systems, they are combined. Understanding this distinction is key to designing systems that can operate effectively over time. Now, let's explore why continuous systems are so important. As highlighted on page 3 of the document, they enable automation at scale. Instead of requiring manual intervention for every task, continuous systems can handle workflows independently. This is especially important for processes that repeat or evolve over time. Another key benefit is support for ongoing workflows. Many real-world processes span hours, days, or even longer. Continuous systems can manage these extended workflows without interruption. They also enable real-world reactivity. By continuously monitoring data, user actions, and system events, they can respond instantly to changes. This makes them highly dynamic and adaptable. And finally, continuous systems are the foundation of autonomous AI. They provide the infrastructure needed for agents to operate independently, make decisions, and take action without human input. This is what transforms AI from a reactive tool into a proactive system. Now let's focus on one of the core concepts behind continuous systems, event-driven agents. As shown on page 4 of the document, These agents do not wait for human prompts. Instead, they are triggered by events happening in the system or environment. For example, when new data arrives, an agent can process it immediately. When a user performs an action, the system can respond in real time. When a system alert is triggered, such as a threshold breach, the agent can take corrective action. This creates a reactive system that is always listening and ready to act. Event-driven agents are powerful because they enable real-time responsiveness. They ensure that the system reacts immediately to changes, rather than waiting for manual input. This is a key characteristic of modern AI systems, being able to operate autonomously in dynamic environments. Finally, let's look at the architecture that supports these agents. As illustrated on page 5 of the document, event-driven architecture follows a simple but powerful flow. An event occurs, a trigger fires, the agent processes the event, and an action is executed. This decoupled design is critical. Each component operates independently, which makes the system more flexible and scalable. Instead of tightly coupling components, we allow them to react to events as they happen. This enables real-time responsiveness and horizontal scalability. Systems can grow and evolve without needing to redesign the entire architecture. Event-driven architecture is what makes continuous systems possible. It provides the foundation for building systems that are always on, always listening, and always ready to act. And this is what enables true autonomy in AI systems. Now let's look at how continuous systems are activated through scheduling and triggers. As shown on page 6 of the document, there are two primary mechanisms: time-based triggers and event-based triggers. Time-based triggers rely on schedules, often implemented using cron jobs. These are used for predictable, recurring tasks such as generating hourly reports or running nightly batch processes. Another variation is delayed execution, where tasks are scheduled to run after a specific interval or deadline. On the other hand, event-based triggers respond to real-time signals. These include webhooks, where external systems send HTTP callbacks when an event occurs, and message queues like Kafka or SQS, which deliver triggers asynchronously. In production systems, these approaches are often combined. For example, a system may run on a schedule, but also listen for events that require immediate action. This hybrid approach ensures both reliability and responsiveness. Scheduling provides consistency, while event-driven triggers provide real-time adaptability. Now let's explore persistent workflows, one of the defining features of long-running systems. As highlighted on page 7 of the document, persistent workflows are designed to survive over time. Unlike stateless functions that execute once and terminate, persistent workflows maintain context across multiple runs. This means they can resume after interruptions, survive system restarts, and continue executing even after long pauses. This capability is essential for workflows that span extended periods, such as multi-day processes or complex pipelines. For example, a workflow might start processing data, pause while waiting for new input, and then resume when that input becomes available. Persistent workflows ensure that progress is not lost. They maintain continuity, allowing systems to handle long-term tasks reliably. This is a critical requirement for production AI systems, where workflows must operate continuously and handle interruptions gracefully. At the heart of persistent workflows is state management. As illustrated on page 8 of the document, state is essentially the memory of a workflow. It keeps track of what has been done, what is pending, and what context is needed for the next step. Effective state management involves several key components. First, tracking execution progress, knowing which step the workflow is currently in. Second, storing intermediate results, capturing outputs that may be needed later in the process. Third, managing context, ensuring that the system retains relevant information across long-running tasks. And finally, ensuring consistency. This includes handling idempotency, where repeated executions produce the same result, and avoiding duplicate actions. Without proper state management, long-running systems become unreliable and difficult to debug. With it, they become predictable, recoverable, and scalable. State is what enables continuity in autonomous systems. Now let's bring everything together and talk about autonomous agents. As shown on page 9 of the document, these agents operate through a continuous loop of decision-making and execution. They observe their environment, reason about what needs to be done, and take action, all without waiting for human input. This loop repeats continuously, allowing the system to adapt to new information and changing conditions. Another key aspect is continuous monitoring. Autonomous agents constantly watch for signals, anomalies, or opportunities. When something relevant occurs, they respond immediately. Over time, these systems can also improve. By incorporating feedback signals, they refine their decisions and optimize their behavior. This creates self-improving workflows. Autonomous agents represent the next evolution of AI systems, moving from reactive tools to proactive, independent systems capable of driving outcomes on their own. Finally, let's talk about reliability, because long-running systems must be designed to handle failure. As emphasized on page 10 of the document, failure is inevitable in production environments. The goal is not to avoid failure, but to design systems that recover gracefully. One key strategy is retries with backoff. When a task fails, the system retries it with increasing delays, reducing the risk of overwhelming external systems. Another important concept is checkpointing. By saving progress at key stages, the system can resume from the last successful point instead of restarting from scratch. Health monitoring is also critical. This includes heartbeats, watchdogs, and alerting mechanisms that ensure the system is running correctly. Together, these strategies create resilient systems that can operate continuously despite challenges. Reliability is not an afterthought. It is a core requirement for building autonomous AI systems that can function in real-world environments. Let's wrap up this module by reinforcing the most important ideas about continuous and autonomous AI systems. The first key takeaway is this: continuous systems enable automation at scale. As highlighted on the slide, these systems remove the need for constant human input. Instead of triggering actions manually, workflows run continuously in the background. This allows AI systems to handle complex, recurring tasks efficiently and consistently. It's what transforms AI from a tool into an always-on system. The second takeaway is the importance of event-driven agents. Event-driven systems react to the world in real time. Instead of waiting for instructions, they respond to signals such as new data, user actions, or system alerts. This decoupled design allows systems to operate independently and scale efficiently. It also ensures that the system remains responsive and adaptive to changing conditions. The third takeaway is that scheduling powers predictable automation. As we saw earlier, time-based triggers such as cron jobs ensure that tasks run at regular intervals. Combined with event-driven triggers, they create systems that are both reliable and responsive. Scheduling provides structure, while events provide flexibility. Together, they form the backbone of continuous execution. The fourth takeaway is persistence and state management. Long-running systems must maintain context over time. This includes tracking progress, storing intermediate results, and ensuring consistency across executions. Without persistence, workflows would restart from scratch every time. With proper state management, systems can resume, recover, and continue seamlessly, even after interruptions. And finally, the most important insight: autonomous agents drive production AI systems. As emphasized on the slide, these agents operate through continuous loops of observation, reasoning, and action. They monitor environments, detect changes, and respond without waiting for human input. Combined with reliability engineering, such as retries, checkpointing, and monitoring, they become robust, real-world systems capable of delivering value continuously. So as you move forward, remember this: don't just build systems that respond, build systems that run, systems that monitor, systems that adapt, and systems that act continuously. Because the future of AI is not one-time intelligence. It's autonomous, always-on systems that never stop working. In this module, we explore one of the most powerful concepts in modern AI systems: feedback loops. Because true intelligence is not just about generating outputs, it's about improving from them. As introduced in your material, feedback loops represent a fundamental shift from static pipelines to adaptive, self-improving systems. Traditional AI systems follow a simple pattern. Input goes in, output comes out, and the process stops there. But feedback loops close this cycle. They take outputs and route them back into the system as new inputs, enabling continuous learning. This transforms AI from a one-time inference engine into a system that evolves over time. As highlighted on page 2, this is the transition from static systems to adaptive systems, and ultimately to autonomous AI. These systems don't just respond, they learn from every interaction, and that is what makes them increasingly accurate, reliable, and valuable over time. Now let's understand why feedback loops are so important. They drive 3 major outcomes: improved accuracy, reduced errors, and continuous optimization. First, accuracy. With every iteration cycle, the system learns from past outputs and improves its responses. This creates a compounding effect. Small improvements over time lead to significant gains in performance. Second, reducing errors. By capturing error signals and feeding them back into the system, we can identify and correct incorrect outputs. This reduces drift and improves reliability. And third, optimization. Feedback loops enable continuous tuning of the system. There is no fixed endpoint. Systems keep improving as long as feedback is available. This is what makes them fundamentally different from static models. Feedback loops turn AI into a learning system rather than a fixed one. And this is essential for building production-grade, adaptive AI systems. At the heart of feedback loops is the idea that every output is a data point. Learning from outputs involves 4 key steps: analyzing responses, capturing signals, evaluating quality, and storing results for improvement. When the system generates an output, it doesn't just move on, it analyzes that output. Was it correct? Was it useful? Did it meet the user's intent? Next, the system captures signals. These signals can indicate success or failure, providing valuable information about performance. Then comes evaluation. Outputs are assessed based on quality metrics such as accuracy, relevance, or user satisfaction. Finally, the results are stored in memory or logs, creating a dataset for future improvement. This creates a flywheel effect where every output contributes to improving the next one. This is what enables measurable quality gains across system iterations. Not all feedback is the same, and understanding different types is critical for building robust systems. Feedback can be categorized into 4 types: explicit, implicit, system, and combined. Explicit feedback comes directly from users, such as ratings, corrections, or annotations. This is highly valuable because it provides clear signals about what works and what doesn't. Implicit feedback is derived from user behavior, such as clicks, dwell time, or query reformulations. While less direct, it provides rich insights into how users interact with the system. System feedback includes logs, latency metrics, confidence scores, and error traces. This helps monitor system performance and identify technical issues. Finally, combined feedback integrates all these signals to create a more complete picture. No single source tells the full story. The most effective systems combine multiple feedback types to achieve the highest signal quality. Not all feedback is the same, and understanding different types is critical for building robust systems. Feedback can be categorized into 4 types: explicit, implicit, system, and combined. Explicit feedback comes directly from users, such as ratings, corrections, or annotations. This is highly valuable because it provides clear signals about what works and what doesn't. Implicit feedback is derived from user behavior, such as clicks, dwell time, or query reformulations. While less direct, it provides rich insights into how users interact with the system. System feedback includes logs, latency metrics, confidence scores, and error traces. This helps monitor system performance and identify technical issues. Finally, combined feedback integrates all these signals to create a more complete picture. No single source tells the full story. The most effective systems combine multiple feedback types to achieve the highest signal quality. Now let's move into how systems actually improve over time, through iteration. Iterative improvement means continuously refining the system based on feedback signals. Instead of making one large change and hoping for the best, we apply small, consistent updates that gradually enhance performance. One of the most common methods is prompt refinement. By analyzing failure patterns, we can adjust instructions to produce better outputs. Another approach is parameter tuning, modifying settings like temperature or sampling strategies to control output behavior. Beyond that, workflows themselves can be updated. This includes improving tool selection, refining routing logic, or adjusting how agents make decisions. Finally, experimentation plays a key role. Every improvement follows a loop. Form a hypothesis, test it, measure the results, and deploy if successful. This iterative cycle is what enables systems to evolve steadily and reliably over time. Now let's talk about adaptive systems. Systems that don't just improve offline, but adjust in real time. Adaptive systems learn from past interactions and use that knowledge to influence future behavior. This means the system evolves dynamically, without requiring constant redeployment. One key capability is personalization. The system can tailor responses based on user history, preferences, or past interactions. Another is context awareness. Instead of treating each interaction independently, the system uses prior context to make more informed decisions. Adaptive systems can also modify their behavior based on feedback signals, changing how they respond, which tools they use, or how they prioritize tasks. This creates a system that becomes more aligned with user needs over time. The key idea is evolution. Adaptive systems don't remain static. They continuously adjust and improve as they interact with the world. Now, let's explore how systems decide what to improve through reinforcement and optimization. Every output generated by the system can be evaluated and assigned a signal. High-quality outputs receive positive signals, while incorrect or low-quality outputs receive negative signals. These signals guide the system's future behavior. This concept is inspired by reinforcement learning, where decisions are shaped by rewards and penalties. However, in modern AI systems, this doesn't always require full model retraining. Instead, we can update prompts, adjust workflows, or modify decision logic based on accumulated signals. Over time, this creates a feedback-driven optimization loop. good behaviors are reinforced and poor behaviors are reduced. This process continuously improves system performance without requiring major changes. It's a powerful way to evolve systems incrementally while maintaining stability. For feedback loops to work effectively, we must measure performance consistently. Monitoring and evaluation provide the visibility needed to understand how the system is performing. This includes tracking key metrics such as latency, accuracy, and error rates. These metrics help identify issues like performance degradation or increased error frequency. Another important technique is A/B testing. By comparing different versions of prompts, workflows, or system configurations, we can determine which approach performs better. Feedback analytics also play a crucial role. By aggregating signals from users, system logs, and performance data, we can extract actionable insights. Without monitoring, feedback loops become blind. We don't know what is improving or what is failing. Measurement is what drives optimization. It ensures that improvements are data-driven rather than guesswork. Let's step back and look at the bigger picture. Feedback loops are not just about improving individual components. They are about creating self-improving systems. When feedback is consistently captured, analyzed, and applied, the system begins to evolve on its own. This transforms AI from a static system into a dynamic one. Instead of requiring manual updates, the system continuously adapts based on real-world usage. Over time, this leads to compounding improvements in accuracy, reliability, and user experience. This is the foundation of autonomous AI systems, systems that learn, adapt, and improve without constant human intervention. Feedback loops are what make this possible. They close the gap between output and learning, creating a cycle of continuous improvement. And this is what defines the next generation of AI systems, systems that don't just perform tasks, but get better at them over time. Let's wrap up this module by reinforcing the most important ideas about feedback loops and self-improving AI systems. The first key takeaway is this: feedback enables continuous learning. Every output generated by the system is not just a result, it's a learning opportunity. By capturing signals from outputs and feeding them back into the system, we create a continuous learning loop. This transforms AI from a static system into one that evolves over time. The second takeaway is the power of iteration. As we discussed, improvement does not come from one major change. It comes from small, consistent refinements. By continuously adjusting prompts, tuning parameters, and improving workflows, the system gradually becomes more accurate and reliable. These incremental improvements compound over time, leading to significant gains in performance. The third takeaway is that adaptive systems evolve dynamically. Adaptive systems don't require constant redeployment or manual updates. Instead, they learn from interactions and adjust their behavior in real time. This includes personalization, context awareness, and dynamic decision-making. The system becomes more aligned with user needs as it gathers more data. The fourth takeaway is the importance of monitoring and measurement. You cannot improve what you do not measure. Monitoring performance metrics, analyzing feedback signals, and running experiments are essential for understanding system behavior. This ensures that improvements are data-driven and that the system continues to evolve in the right direction. And finally, the most important insight: self-improving AI is the future. As feedback loops become more advanced, AI systems will increasingly operate as autonomous learning systems. They will continuously refine their behavior, optimize their decisions, and adapt to changing environments without constant human intervention. So as you move forward, remember this: don't just build systems that generate outputs. Build systems that learn from them, systems that improve, systems that adapt, and systems that evolve over time. Because the true power of AI is not just intelligence, it's continuous improvement. In this module, we focus on one of the most critical, yet often overlooked aspects of building AI systems: debugging. Because no matter how advanced your system is, it will fail. And how you handle those failures determines whether your system is reliable or unusable. Debugging AI systems is fundamentally different from traditional software debugging. In traditional systems, the same input produces the same output, making issues easier to reproduce and fix. But in AI systems, behavior is probabilistic. The same input may produce different outputs at different times. This makes failures harder to detect, reproduce, and diagnose. Additionally, AI systems are multi-layered. Failures can occur in prompts, models, retrieval pipelines, tool execution, or orchestration logic. And often, the issue is not in a single component, but in how multiple components interact. This complexity is what makes debugging AI systems a unique challenge. It requires new thinking, new tools, and a structured approach to identifying and resolving issues. Now let's explore why AI systems fail in the first place. As highlighted in the material, failures are rarely caused by a single issue. They are often the result of multiple interacting factors. One major reason is system complexity. AI systems are composed of multiple components: models, retrievers, tools, and orchestration layers, and failures can cascade across these components. Another common issue is model hallucination. Models can generate outputs that sound confident and plausible, but are factually incorrect. These errors are particularly dangerous because they are not obvious. Data and context issues also play a significant role. If the system is given incomplete, outdated, or poorly formatted information, the output will be affected. Finally, integration failures occur when external tools or APIs return unexpected results, errors, or timeouts. These issues can disrupt the entire workflow. Understanding these failure modes is the first step toward effective debugging. You cannot fix what you do not understand. Now let's look at how these failures actually appear in practice. One of the most important insights is that AI failures rarely look like crashes. Instead, they appear as outputs that seem correct, but are actually wrong. These are subtle failures that require careful analysis. One common pattern is reasoning failure, where the model's logic breaks down mid-process. The conclusion may not follow from the premises, leading to incorrect results. Another pattern is context failure, where the system lacks the necessary information to produce a correct answer. This often happens when retrieval systems return irrelevant or incomplete data. A third pattern is consistency failure. Because AI systems are non-deterministic, the same input can produce different outputs, masking deeper instability. And finally, tool misuse, where the system selects the wrong tool or passes incorrect parameters. Recognizing these patterns is essential for diagnosing issues effectively. Once you can identify the type of failure, you can begin to trace it back to its root cause. Let's now focus on one of the most common issues: reasoning failures. Debugging these requires a structured approach. The first step is to inspect the prompt and output. You need to log the full prompt and compare the expected reasoning with the actual output. This helps identify where things start to go wrong. The next step is to locate the breakpoint, the exact point where the logic diverges. This could be due to ambiguous instructions, missing constraints, or formatting issues. Once the issue is identified, the next step is refinement. This involves improving the prompt by adding clearer instructions, examples, or constraints to guide the model. Finally, validation is critical. You need to verify each step of the reasoning process independently to ensure that the logic holds. This step-by-step validation ensures that the system produces reliable and consistent outputs. Debugging reasoning is not about guessing. It's about systematically identifying and fixing the root cause. Another major source of failure lies in retrieval and memory systems. When these components fail, the entire system can produce incorrect results, even if the model itself is working correctly. One common issue is retrieving the wrong or missing data. If the system pulls irrelevant or incomplete information, the model will generate poor outputs. Another issue is poor embedding quality. If the embedding model does not capture semantic meaning effectively, retrieval results will be inaccurate. Context overload is also a common problem. Providing too much information can dilute the signal, making it harder for the model to focus on relevant details. To address these issues, we need to improve the retrieval pipeline. This can include re-ranking results, combining multiple search strategies, and applying metadata filtering. By refining how data is retrieved and presented, we can significantly improve system performance. Debugging retrieval is about ensuring that the model has the right information at the right time. Now let's move into one of the most important foundations of debugging, logging. Without proper logging, debugging AI systems becomes nearly impossible. As emphasized in the material, you must capture everything. This includes inputs, outputs, intermediate steps, and decisions made by the system. Every prompt sent to the model and every response generated should be recorded. In addition to that, tool calls must also be logged. This means capturing the function name, the arguments passed, the response returned, and even the latency of each call. Errors and failures should be tagged clearly so they can be traced back to their origin. The key idea here is traceability. If you cannot replay a failure, you cannot fix it. Logging creates a complete record of system behavior, allowing you to analyze what went wrong and why. It turns debugging from guesswork into a systematic process. Building on logging, we now move to observability and monitoring. Logging tells you what happened. Observability helps you understand how the system is performing over time. This involves tracking key metrics such as latency, accuracy, and error rates. Latency metrics help identify performance bottlenecks across different components, such as model inference, retrieval, or tool execution. Accuracy metrics track the quality of outputs, helping detect degradation or drift over time. Error rates provide insight into how frequently failures occur and where they originate. Observability also includes dashboards and alerting systems. Dashboards provide a visual overview of system health, while alerts notify you when something goes wrong, such as a spike in errors or a drop in performance. Together, these tools provide real-time visibility into your system. Without observability, you are operating blind. With it, you can detect issues early and respond proactively. Now let's talk about testing, your first line of defense against failures. As highlighted in the material, testing in AI systems must be multi-layered. The first layer is unit testing. This focuses on individual components such as tools, functions, and parsers, ensuring that each part works correctly in isolation. The second layer is integration testing. This validates how different components interact with each other, ensuring that data flows correctly across the system. And finally, scenario-based testing. This involves testing real-world use cases, including edge cases and adversarial inputs. These tests help uncover failures that only appear in complex or unexpected situations. The key idea is coverage. Each layer of testing addresses a different type of failure. Together, they create a safety net that catches issues before they reach production. Testing is not a one-time activity. It must be continuous and evolve with the system. Now, let's focus on debugging entire workflows where multiple components interact. Debugging workflows requires a step-by-step approach. The first step is inspection. You log inputs and outputs at every stage of the pipeline, ensuring visibility into each step. The second step is isolation. You identify which component is causing the failure by narrowing down the pipeline. This often involves testing individual components independently. The third step is reproduction. You capture the full context of the failure, allowing you to recreate the issue consistently. This is critical for effective debugging. And finally, iteration. Once the issue is fixed, you rerun the workflow and validate the fix through testing. This structured approach ensures that issues are identified and resolved systematically. Debugging workflows is about understanding the system as a whole, not just individual components. Now let's focus on debugging entire workflows, where multiple components interact. Debugging workflows requires a step-by-step approach. The first step is inspection. You log inputs and outputs at every stage of the pipeline, ensuring visibility into each step. The second step is isolation. You identify which component is causing the failure by narrowing down the pipeline. This often involves testing individual components independently. The third step is reproduction. You capture the full context of the failure, allowing you to recreate the issue consistently. This is critical for effective debugging. And finally, iteration. Once the issue is fixed, you rerun the workflow and validate the fix through testing. This structured approach ensures that issues are identified and resolved systematically. Debugging workflows is about understanding the system as a whole, not just individual components. Let's step back and look at the bigger picture. Debugging is not just about fixing errors. It's about improving the system. Every failure provides valuable insight into how the system behaves and where it can be optimized. By analyzing failures, we can refine prompts, improve retrieval pipelines, optimize tool execution, and enhance overall system design. Over time, this process leads to more robust and reliable systems. Debugging becomes a continuous process of learning and improvement. This is what transforms debugging into optimization. Instead of reacting to issues, we proactively improve the system based on observed behavior. This mindset is essential for building production-grade AI systems, because in real-world environments, systems must not only work, they must continuously improve. In this module, we focus on one of the most critical aspects of building production AI systems: optimization. Because moving from prototype to production is not just about making systems work, it's about making them efficient, fast, and scalable. As highlighted in the engineering guide, every production AI system must balance 4 key dimensions: speed, accuracy, cost, and scale. These are not independent, they are trade-offs. Increasing accuracy often increases cost. Reducing latency may require simpler models. Scaling systems introduces infrastructure complexity. Optimization is the discipline of managing these trade-offs intentionally. It's about designing systems that deliver acceptable performance while staying within cost and latency constraints. This is what separates experimental systems from production-ready systems. In real-world environments, optimization is not optional, it is essential. Without it, systems become too slow, too expensive, or too difficult to scale. To optimize effectively, we must first understand what drives cost in AI systems. The most significant factor is token usage. Every input and output token contributes directly to cost, which means every word matters. Large prompts and long responses quickly increase expenses, especially at scale. Another major factor is model selection. More powerful models deliver higher quality, but they can be significantly more expensive per token. Choosing the right model for the task is critical. Tool and API calls also contribute to cost. Every external request introduces additional latency and often per-call charges. Finally, infrastructure costs, such as compute, memory, and data transfer, scale with usage. As systems grow, these costs compound rapidly. The key takeaway is that cost is not driven by a single factor. It is the result of multiple interacting components. Understanding these drivers allows us to identify where optimization efforts will have the greatest impact. Now let's focus on the most direct lever for cost reduction: token efficiency. Since tokens are the primary billing unit, reducing token usage has an immediate impact on cost. One of the most effective strategies is reducing prompt size. Prompts should be stripped down to their essential intent, removing unnecessary instructions or verbose language. Another important technique is avoiding unnecessary context. Only include information that directly contributes to the task. Including irrelevant context not only increases cost, but can also degrade performance. Caching is another powerful strategy. If the same or similar query is processed multiple times, the result can be reused instead of recomputed. Finally, efficient prompt design plays a key role. Structured prompts, such as bullet points or schemas, tend to be more concise and consistent than long-form text. By focusing on token efficiency, we can significantly reduce cost without sacrificing performance. Now let's focus on the most direct lever for cost reduction: token efficiency. Since tokens are the primary billing unit, reducing token usage has an immediate impact on cost. One of the most effective strategies is reducing prompt size. Prompts should be stripped down to their essential intent, removing unnecessary instructions or verbose language. Another important technique is avoiding unnecessary context. Only include information that directly contributes to the task. Including irrelevant context not only increases cost, but can also degrade performance. Caching is another powerful strategy. If the same or similar query is processed multiple times, the result can be reused instead of recomputed. Finally, efficient prompt design plays a key role. Structured prompts, such as bullet points or schemas, tend to be more concise and consistent than long-form text. By focusing on token efficiency, we can significantly reduce cost without sacrificing performance. Finally, let's look at context management, one of the most overlooked cost drivers in AI systems. The context window is expensive real estate. Every additional token increases cost, and bloated context is one of the most common inefficiencies in production systems. One key strategy is limiting the context window. This involves capping the number of tokens passed to the model and ensuring that only relevant information is included. Another technique is chunking and summarization. Instead of passing entire histories or large documents, we compress them into smaller summaries that retain essential information. Dynamic context injection is also important. Rather than including all possible context up front, we retrieve and inject context only when it is needed. These strategies ensure that the model receives the right information at the right time, without unnecessary overhead. Effective context management improves both performance and cost efficiency. Now let's focus on latency, because performance is not just about correctness, it's about speed. As highlighted in the guide, every millisecond of delay is felt by users. Slow systems create poor user experience, reduce engagement, and limit real-world adoption. One of the most effective ways to reduce latency is eliminating sequential dependencies. When tasks are executed one after another unnecessarily, delays accumulate quickly. Instead, we should design systems to run tasks in parallel wherever possible. Parallelizing tool calls allows multiple operations to execute at the same time, significantly reducing total response time. Another key technique is streaming responses. Rather than waiting for the entire output to be generated, responses can be delivered incrementally, reducing perceived latency. Finally, model selection plays a critical role. Choosing a faster model for simpler tasks can dramatically improve performance without sacrificing quality. Latency optimization is about designing systems that respond quickly and efficiently, creating a smooth user experience. Now let's focus on latency, because performance is not just about correctness, it's about speed. As highlighted in the guide, every millisecond of delay is felt by users. Slow systems create poor user experience, reduce engagement, and limit real-world adoption. One of the most effective ways to reduce latency is eliminating sequential dependencies. When tasks are executed one after another unnecessarily, delays accumulate quickly. Instead, we should design systems to run tasks in parallel wherever possible. Parallelizing tool calls allows multiple operations to execute at the same time, significantly reducing total response time. Another key technique is streaming responses. Rather than waiting for the entire output to be generated, responses can be delivered incrementally, reducing perceived latency. Finally, model selection plays a critical role. Choosing a faster model for simpler tasks can dramatically improve performance without sacrificing quality. Latency optimization is about designing systems that respond quickly and efficiently, creating a smooth user experience. Now let's explore one of the highest impact optimization techniques: caching. As emphasized in the guide, caching is often the fastest way to reduce both cost and latency without changing the model itself. The core idea is simple: don't compute what you've already computed. If a system receives the same or similar request multiple times, the result can be stored and reused instead of recalculating it. This applies not only to full responses, but also to intermediate results such as embeddings. Pre-computing and storing embeddings allows systems to skip expensive computations during runtime. Another important aspect is deduplication. When multiple requests perform identical operations, we can consolidate them to avoid redundant work. The impact of caching is significant. Cached responses can be returned in milliseconds, compared to seconds for full model inference. This improves both performance and cost efficiency. Caching is one of the simplest yet most powerful optimization strategies in production AI systems. Optimization is only possible when we can measure performance. As emphasized in the guide, you cannot optimize what you cannot measure. Monitoring involves tracking key metrics such as latency, throughput, and cost. Latency metrics help us understand how quickly the system responds, while throughput measures how many requests can be handled over time. Cost metrics track token usage and resource consumption, providing visibility into spending. Another important aspect is identifying bottlenecks. By tracing system behavior, we can pinpoint slow components, expensive operations, or inefficient workflows. Observability tools, dashboards, and alerts provide real-time insights into system health. This allows teams to detect issues early and respond proactively. Monitoring is not a one-time setup. It must be continuous. It is the foundation of all optimization efforts. Optimization is only possible when we can measure performance. As emphasized in the guide, you cannot optimize what you cannot measure. Monitoring involves tracking key metrics such as latency, throughput, and cost. Latency metrics help us understand how quickly the system responds, while throughput measures how many requests can be handled over time. Cost metrics track token usage and resource consumption, providing visibility into spending. Another important aspect is identifying bottlenecks. By tracing system behavior, we can pinpoint slow components, expensive operations, or inefficient workflows. Observability tools, dashboards, and alerts provide real-time insights into system health. This allows teams to detect issues early and respond proactively. Monitoring is not a one-time setup. It must be continuous. It is the foundation of all optimization efforts. Let's wrap up this module by reinforcing the most important ideas about performance and cost optimization in AI systems. The first key takeaway is this: optimization is a balancing act. As we discussed throughout the module, every AI system must balance speed, accuracy, cost, and scalability. Improving one dimension often impacts another. For example, using a more powerful model may improve accuracy but increase cost and latency. Optimization is about making intentional trade-offs based on your system's goals and constraints. There is no one-size-fits-all solution, only the right balance for your use case. The second takeaway is the importance of token efficiency. Tokens are the primary cost driver in most AI systems. Every input and output contributes to total spend. By reducing prompt size, removing unnecessary context, and designing efficient prompts, we can significantly lower costs without sacrificing quality. Small improvements in token usage can lead to massive savings at scale. The third takeaway is that latency is a user experience problem. Users don't just care about correctness, they care about speed. Even small delays can impact engagement and satisfaction. Techniques like streaming responses, parallel execution, and choosing faster models can dramatically improve responsiveness. Performance is not just a technical metric, it directly affects how users perceive your product. The fourth takeaway is scalability enables growth. As your system grows, it must handle more users, more requests, and more complexity. Designing for scalability from the beginning ensures that your system can expand without breaking or becoming too expensive. Horizontal scaling, load balancing, and distributed architectures are essential for handling growth efficiently. And finally, the most important insight: optimization is continuous. There is no final optimized state. Systems evolve, workloads change, and new inefficiencies emerge over time. This means optimization must be an ongoing process. By continuously monitoring performance, analyzing costs, and iterating on improvements, we ensure that the system remains efficient and effective. So as you move forward, remember this: don't just build AI systems that work. Build systems that scale, systems that are fast, systems that are cost efficient, and systems that continuously improve over time. Because in production AI, performance is not optional. It's what determines success. Let's begin by reflecting on your journey throughout this course. You started with simple tools, the basic building blocks of AI systems. From there, you moved into workflows, where individual steps were orchestrated into repeatable processes. Then you progressed to agents, autonomous units capable of reasoning, acting, and interacting with tools. And finally, you reached systems, integrated, scalable architectures that bring everything together. This progression is not just about learning new concepts. It represents a transformation in how you think about AI. Each stage built on the previous one, expanding your perspective from isolated components to complete systems. And this is the most important shift, understanding that real-world AI is not about individual tools, but about how everything connects. Now let's look at what you've actually built during this journey. You've created AI agents that can reason, make decisions, and execute tasks using tools. You've explored multi-agent systems, where specialized agents collaborate to solve complex problems. You've designed memory and retrieval systems, enabling context-aware intelligence that persists over time. And most importantly, you've built end-to-end workflows, complete systems that take inputs, process them intelligently, and deliver outputs. These are not theoretical concepts. These are real-world system patterns used in production AI. What you've built forms the foundation of modern AI engineering. And this is what differentiates you. You're not just learning AI, you're building systems that can actually be deployed. Let's now summarize the most important takeaways from this course. First, architecture thinking comes before model selection. The best systems are not defined by the model they use, but by how they are designed. Second, integration matters more than individual components. A well-connected system outperforms a collection of powerful but disconnected tools. And third, systems win in the long term. Individual tools may change, models may evolve, but well-designed systems endure. These principles are what guide successful AI development. They shift your focus from short-term experimentation to long-term system design. And this is what defines professional-level AI engineering. This brings us to the most important transformation in this course, the shift from builder to architect. A builder focuses on individual components, solving specific problems one piece at a time. An architect, on the other hand, designs complete systems. They think about scalability, reliability, integration, and performance from the beginning. The difference is not just technical, it's a mindset shift. Architects think in terms of workflows, interactions, and system behavior over time. They design systems that can grow, adapt, and handle real-world complexity. This shift is what elevates your skill set. It's not about learning more tools, it's about thinking differently. Finally, let's talk about the mindset that defines an AI architect: system thinking. This means understanding how every component interacts within the system. It means designing end-to-end flows, tracing data from input to output, and ensuring that every step works together seamlessly. It also means anticipating failures, designing for edge cases, timeouts, and unexpected behavior. And importantly, it means optimizing for real-world constraints such as performance and cost. System thinking is what allows you to build robust, scalable, and production-ready AI systems. It's the mindset that turns ideas into systems, and systems into real-world impact. Now let's connect everything you've learned to the real world. The systems you've built are not just theoretical, they directly map to real-world applications. One major category is AI copilots and assistants, which help users perform tasks more efficiently across domains like coding, writing, and decision-making. Another is business automation, where AI systems handle repetitive workflows, reducing manual effort and increasing productivity. Data and analytics systems are another key area, where AI processes large volumes of data to generate insights and support decision-making. And finally, autonomous AI platforms represent the most advanced use case: systems that operate continuously, monitor environments, and take action independently. These applications show that AI systems are not limited to one industry. They are becoming foundational across all domains. This is where your skills become valuable, when you can translate concepts into real-world solutions. Let's go deeper into how these systems are used across industries. One of the most impactful use cases is customer support automation, where AI systems provide 24/7 assistance, resolving queries at scale while maintaining consistency. Another is content generation systems, which produce high-quality, on-brand content at volume, used in marketing, media, and communications. In the development space, AI-powered tools enhance productivity through code generation, review, and debugging assistance. And in operations and decision-making, AI systems analyze data and generate insights that drive business strategy. These use cases demonstrate a key point. AI is not just about intelligence, it's about impact. Systems that integrate into workflows and solve real problems are the ones that deliver value. Now let's talk about where this journey can take you. The skills you've built open up multiple high-demand career paths. One path is becoming an AI engineer, focusing on building and deploying models and systems. Another is AI systems architect, where you design full-scale AI systems and workflows. You could also pursue a role as an ML engineer, working on model training, optimization, and data pipelines. And finally, there's the AI product builder, someone who takes these technologies and turns them into real-world products. These roles reflect the growing demand for professionals who understand not just models, but systems. And that's exactly what you've developed in this course. Now the question is, what comes next? The most important step is to build real projects. Apply what you've learned to solve real problems. This is where your understanding deepens and your skills become tangible. Next, build your portfolio. Document your projects, your architecture decisions, and the results you achieve. This becomes your proof of capability. Contributing to open source is another powerful step. It helps you learn from others, get feedback, and grow faster. And finally, keep advancing. AI systems are evolving rapidly, and continuous learning is essential. Explore advanced topics, experiment with new tools, and keep building. Growth comes from consistent action. Let's close with one final message. AI is no longer just a field of study. It's a system design discipline. The future belongs to those who can build systems that are scalable, reliable, and impactful. What you've learned in this course is not just knowledge, it's a way of thinking, a way of approaching problems, designing solutions, and delivering value. So keep building, keep experimenting, keep pushing your ideas into real systems, because the people shaping the future of AI are not waiting, they are building, and now you're one of them. Let's close this course by reinforcing the most important ideas that you should carry forward. The first key takeaway is this: AI is a system design discipline. Throughout this journey, you've seen that real-world AI is not about isolated models or individual tools. It's about designing systems that connect components, manage workflows, handle failures, and deliver consistent outcomes. This shift in thinking is what separates beginners from professionals. The second takeaway is the importance of thinking in systems, not features. It's easy to focus on building a single feature or solving a specific problem. But real impact comes from understanding how everything connects, how data flows, how decisions are made, how outputs are generated, and how the system behaves over time. This system-level thinking is what allows you to build scalable and reliable solutions. The third takeaway is this: integration and execution matter more than ideas. Many people have ideas. Many people experiment with AI. But the ones who succeed are those who can take an idea and turn it into a working system, something that runs, scales, and delivers value in real-world environments. Execution is what creates impact. The fourth takeaway is continuous improvement. The systems you build will never be perfect, and that's okay. What matters is that they improve over time. Through feedback loops, optimization, debugging, and iteration, your systems become more accurate, more efficient, and more reliable. Growth is built into the system. And finally, the most important insight: you are now capable of building production AI systems. You've gone beyond theory. You've learned how to design agents, orchestrate workflows, manage memory, integrate tools, and build complete systems. These are real, valuable skills, skills that are in demand and directly applicable in industry. So as you move forward, remember this: don't wait for the perfect idea. Don't wait for permission. Start building. Build systems. solve real problems, and ship things that matter. Because the future of AI is not built by observers. It's built by people like you, who take action. In this module, we shift from building systems to building your future. AI is no longer just a technical field. It's a career ecosystem with multiple paths and opportunities. As highlighted in your guide, AI offers high demand, multiple entry points, and limitless potential. Whether you are more technical or business-oriented, there is a role for you. You can focus on engineering, system design, product development, or even business and freelancing. This flexibility is what makes AI such a powerful career space. The key is not just learning skills, but choosing how you want to apply them. Your journey doesn't end with building systems. It begins with deciding how to use those skills to create value in the real world. Let's start with one of the most common paths, the AI engineer. This is the hands-on builder role. As described in your material, AI engineers are responsible for implementing, integrating, and deploying AI-powered systems. They work on building and deploying models, connecting APIs and data pipelines, and ensuring systems run effectively in production. Another important aspect of this role is bridging the gap between research and real-world applications. AI engineers take theoretical models and turn them into working systems that solve real problems. This role requires both technical depth and practical understanding of system integration. It's ideal for those who enjoy building, experimenting, and working directly with technology. To succeed as an AI engineer, there are a few core skills you need to develop. First is programming, especially Python, and familiarity with cloud platforms like AWS, GCP, or Azure. These are essential for deploying and scaling systems. Second is working with LLMs and AI tools, understanding how to use APIs, embeddings, and vector databases effectively. Third is data handling, building pipelines, managing data, and designing prompts. And finally, debugging and optimization. AI systems are not perfect, so you must continuously improve performance, reduce latency, and manage cost. These skills form the foundation of real-world AI engineering. Mastering them allows you to build systems that are not only functional, but production-ready. Now let's move to a more advanced role, the AI systems architect. This is where the focus shifts from building components to designing complete systems. As outlined in your guide, architects are responsible for end-to-end system design. They think about how data flows through the system, how components interact, and how the system scales. They manage orchestration, ensuring that workflows and agents work together effectively. They also design for scalability and reliability, making sure systems can handle growth and continue to perform under pressure. This role is less about coding individual features and more about designing the big picture. It requires a deep understanding of how systems behave and how to optimize them for real-world use. Finally, let's talk about the mindset that defines an architect. As emphasized in your material, the biggest shift is not technical, it's mental. Architects think in systems, not features. They see the whole picture, not just individual components. Every decision they make has ripple effects across the system. They design for scale and failure, anticipating what might go wrong before it happens. They optimize for cost and performance, understanding that efficiency matters in production. And most importantly, they balance trade-offs. There is no perfect solution, only the best solution for a given context. This mindset is what elevates someone from a builder to an architect. It's about thinking ahead, designing holistically, and building systems that last. Now let's look at one of the most exciting paths, the AI product builder. This role is focused on creating products that people actually use. As highlighted in your guide, This involves combining AI capabilities with front-end and back-end systems to deliver real-world applications. AI product builders don't just focus on technology, they focus on user experience. The goal is not to impress with complexity, but to solve problems effectively. This requires full-stack thinking, understanding how AI integrates with interfaces, workflows, and business needs. You are responsible for the entire product, from idea to execution. This path is ideal for those who want to build startups, launch tools, or create scalable digital products powered by AI. Another powerful path is freelancing. As emphasized in your material, businesses are rapidly adopting AI, but often lack the expertise to implement it. This creates a massive opportunity for freelancers. You can help businesses automate workflows, build custom AI agents, and integrate AI into their existing systems. Freelancing offers flexibility. You can work on diverse projects, gain real-world experience, and earn competitive income. You're not limited to one company or one role. Instead, you become a problem solver for multiple clients. This path is especially valuable early in your career, as it allows you to build experience quickly while getting paid. It's one of the fastest ways to enter the AI industry. Now let's talk about building your own business through SaaS or startups. As highlighted in your guide, AI enables a powerful model. Build once, sell repeatedly. By creating niche AI tools that solve specific problems, you can generate recurring revenue. The key is to find a focused use case, a specific problem for a specific audience. Then build a solution that solves it efficiently using AI. Once the system is built, automation allows it to scale with minimal additional effort. This is where AI becomes not just a skill, but a business opportunity. SaaS and startups represent the highest leverage path, where your systems work for you at scale. Now the question is, how do you choose your path? The first step is to pick a focus area. Whether it's engineering, architecture, or product building, clarity helps you move faster. Next, build real projects. As emphasized in your guide, real-world projects are more valuable than theoretical knowledge. Then, share your work publicly. Posting on platforms like GitHub or LinkedIn helps you build credibility and attract opportunities. Networking and collaboration are also key. Learning from others accelerates your growth. The most important idea here is consistency. Progress comes from continuous action, not perfection. Let's summarize the most important ideas from this module. First, AI offers multiple career paths, from engineering to architecture to business opportunities. Second, systems thinking is a major advantage. The ability to design complete systems sets you apart in the industry. Third, value creation matters. Whether through products, services, or solutions, the goal is to solve real problems. And finally, the best time to start is now. Opportunities in AI are growing rapidly, and those who take action early will have the greatest advantage. This is not just a learning journey, it's a career opportunity waiting to be built.